Chapter 19 Blockchain Outside of Currencies. Digital currencies were the first ever application of blockchain, which arguably didn't realize the technology's full potential. Although Bitcoin, the first major blockchain conceptualization, was introduced in 2008, it was not until years later that blockchain technology's possible applications in industries other than cryptocurrencies were realized. In 2010, discussion started regarding BitDNS, a decentralized naming system for domains on the Internet. Then Namecoin started in April 2011 with a different vision to Bitcoin, the sole purpose of which was to provision electronic cash. This can be considered the first example of blockchain usage other than purely as a cryptocurrency. Next, in 2013, the first initial coin offering, ICO, Mastercoin, emerged, which paved the way for more ICOs. After that, Ethereum's ICO was hugely successful. With the availability of Ethereum in 2015, a general-purpose smart contract platform, more ideas started to emerge around various applications of blockchain technology. Since then, many use cases of blockchain technology in various industries have been proposed. In this chapter, 5 main industries have been selected, with the aid of use cases for discussion: the Internet of Things, government, health, finance, media. Let's begin with one of the most exciting use cases of blockchain technology, the Internet of Things. The Internet of Things. The Internet of Things, IoT, has recently gained much traction due to its potential for transforming business applications and everyday life. IoT can be defined as a network of computationally intelligent physical objects, any objects such as cars, fridges, and industrial sensors, that are capable of connecting to the Internet, sensing real-world events or environments, reacting to those events, collecting relevant data, and communicating this over the Internet. This simple definition has enormous implications and has led to exciting concepts such as wearables, such as health trackers or watches, smart homes, smart grids, smart connected cars, and smart cities, which are all based on this concept of an IoT device. After dissecting the definition of IoT, 4 functions come to light as being performed by an IoT device: sensing, reacting, collecting, and communicating. All of these functions are performed by various components on the IoT device. Sensing is performed by sensors. Reacting or controlling is performed by actuators. Collection is a function of various sensors, and communication is performed by chips that provide network connectivity. One thing to note is that all of these components are accessible and controllable over the Internet via the IoT. An IoT device on its own is useful to some extent, but if it is part of a broader IoT ecosystem, it is more valuable. In the next section, we'll introduce the typical architecture of an IoT-based ecosystem. Internet of Things architecture. A typical IoT can consist of many physical objects connected to each other and to a centralized cloud server. This is shown in the following diagram. Elements of the IoT are spread across multiple layers, and various existing reference architectures can be used to develop IoT systems. A 5-layer model can be used to describe IoT, which contains a physical object layer, device layer, network layer, services layer, and application layer. Each layer or level is responsible for various functions and includes multiple components. These are shown in the following table. Now let's examine each layer in detail. Physical object layer. This layer includes any real-world physical objects. It includes objects like cars, fridges, trains, and homes. In fact, anything that is required to be monitored and controlled can be connected to the IoT. Device layer. This layer contains things that make up the IoT, such as sensors, transducers, actuators, smartphones, smart devices, and radio frequency identification, RFID tags. There can be many categories of sensors such as body sensors, home sensors, and environmental sensors based on the type of work they perform. This layer is the core of an IoT ecosystem, where various sensors are used to sense real-world environments. This layer includes sensors that can monitor temperature, humidity, liquid flow, chemicals, air, pressure, and much more. Usually an analog to digital converter, ADC, is required on a device to turn the real-world analog signal into a digital signal that a microprocessor can understand. Actuators in this layer provide the means to enable control of external environments. For example, starting a motor or opening a door. These components also require digital to analog converters to convert a digital signature into analog. This method is especially relevant when control of a mechanical component is required by the IoT device. Network layer. This layer is composed of various network devices that are used to provide internet connectivity between devices and to the cloud, or servers that are part of the IoT ecosystem. These devices can include gateways, routers, hubs, and switches. This layer can include two types of communication. First, there is the horizontal means of communication, which includes radio, Bluetooth, Wi-Fi, Ethernet, LAN, Zigbee, and PAN, and can be used to provide communication between IoT devices. This layer can optionally be included in the device layer, as it physically resides on the device layer where devices can communicate with each other. Second, we have communication to the next layer, which is usually through the internet and provides communication between machines and people or other upper layers. Management layer. This layer provides the management layer for the IoT ecosystem. This includes platforms that enable the processing of data gathered from the IoT devices and turning it into meaningful insights. Device management, security management, and data flow management are included in this layer. It also manages communication between the device and application layers. Application layer. This layer includes applications running on top of the IoT network. This layer can consist of many applications depending on the requirements, such as transportation, healthcare, financial insurance, or supply chain management. This list, of course, is not an exhaustive list by any stretch of the imagination. There is a myriad of IoT applications that can fall into this layer. With the availability of cheap sensors, hardware, and bandwidth, IoT has gained popularity in recent years, and currently has applications in many different areas including healthcare, insurance, supply chain management, home automation, industrial automation, and infrastructure management. Moreover, advancements in technology such as the availability of IPv6, smaller and more powerful processors, and better internet access have also played a vital role in the popularity of IoT. In the next section, we'll discuss some advantages of IoT and blockchain convergence. Benefits of IoT and blockchain convergence. The benefits of IoT with blockchain technology range from savings costs to enabling businesses to make vital decisions, and thus improve performance based on the data provided by the IoT devices. Even in domestic usage, IoT-equipped home appliances can provide valuable data for cost savings. For example, smart meters for energy monitoring can provide valuable information on how the energy is being used and can convey that back to the service provider. Raw data from millions of IoT devices is analyzed and provides meaningful insights that help in making timely and efficient business decisions. The usual IoT model is based on a centralized paradigm, where IoT devices usually connect to a cloud infrastructure or central servers to report and process the relevant data back. This centralization poses certain possibilities of exploitation, including hacking and data theft. Moreover, not having control of personal data on a single centralized service provider also increases the possibility of security and privacy issues. While there are methods and techniques to building a highly secure IoT ecosystem based on the normal IoT model, there are much more specific and desirable benefits that a blockchain-based model can bring to the IoT. Blockchain for IoT can help to build trust. reduce costs, and accelerate transactions. Additionally, decentralization, which is at the very core of blockchain technology, can eliminate single points of failure in an IoT network. For example, perhaps a central server might be unable to cope with the amount of data that billions of IoT devices, things, produce at high frequency, whereas a decentralized blockchain serving as a communication layer between these IoT devices enables all the IoT devices on the blockchain to maintain a copy of the data store on their own, which means that this architecture is inherently highly available and resilient. Some IoT devices losing their database does not result in the entire network coming to a standstill, as might be the case with a centralized server, even with a disaster recovery solution. Also, the peer-to-peer, P2P communication model provided by blockchain can help reduce costs because there is no need to build high-cost, centralized data centers nor implement complex public key infrastructure for security. Devices can communicate with each other directly or via routers. As an estimate made by various researchers and companies, by 2020 there will be roughly 22 billion devices connected to the Internet. With this explosion of billions of devices connecting to the Internet, it is hard to imagine that centralized infrastructures will be able to cope with the high demands of bandwidth, services, and availability without incurring excessive expenditure. A blockchain-based IoT will be able to solve scalability, privacy, and reliability issues in the current IoT model. Blockchain enables things to communicate and transact with each other directly. And with the availability of smart contracts, negotiation and financial transactions can also occur directly between the devices instead of requiring an intermediary, an authority, or human intervention. For example, if a room in a hotel is vacant, it can rent itself out, negotiate the rent, and can open the door lock for a human who has paid the required fee. Another example could be that if a washing machine runs out of detergent, it could order it online after finding the best price and value based on the logic programmed into its smart contract. The aforementioned 5-layer IoT model can be adapted to a blockchain-based model by adding a blockchain layer on top of the network layer. This layer will run smart contracts and provide security, privacy, integrity, autonomy, scalability, and decentralization services to the IoT ecosystem. The management layer in this case can consist of only software related to analytics and processing, and security and control can be moved to the blockchain layer. This model can be visualized in the following table. In this model, other layers are expected to remain the same, but an additional blockchain layer will be introduced as middleware between all participants of the IoT network. It can also be visualized as a P2P IoT network after abstracting away all the layers mentioned earlier. This model is shown in the following diagram, where all the devices are communicating and negotiating with each other without a central command and control entity. An IoT-based blockchain can also result in cost savings due to the easier device management offered by a blockchain-based decentralized approach. The IoT network can also be optimized for performance by using blockchain. In this case, there will be no need to store IoT data centrally for millions of devices. This is because storage and processing requirements can be distributed to all IoT devices on the blockchain. This can result in completely removing the need for large data centers for processing and storing the IoT data. A blockchain-based IoT can also thwart denial of service (DOS) attacks. Hackers can target a centralized server or data center more efficiently. But with blockchain's distributed and decentralized nature, such attacks are no longer possible. Additionally, if, as estimated, there will soon be billions of devices connected to the Internet, it will become almost impossible to manage security and updates for all those devices from traditional, centrally owned servers. Blockchain can provide a solution to this problem by allowing devices to communicate with each other directly in a secure manner, and even request firmware and security updates from each other. On a blockchain network, these communications can be recorded immutably and securely, which will provide auditability, integrity, and transparency to the system. This mechanism is not possible with traditional P2P systems. In summary, there are clear benefits that can be reaped with the convergence of IoT and blockchain, and a lot of research and work in academia and the industry are already in progress. Practical use cases and platforms have emerged in the form of Platform as a Service, PaaS, for blockchain-based IoT, such as the IBM Watson IoT blockchain. There are various projects that have already been proposed that provide blockchain-based IoT solutions, such as IBM Blue Horizon and IBM Bluemix, two examples of IoT platforms that support blockchain IoT. Various startups such as Filament have already proposed novel ideas on how to build a decentralized network that enables devices on the IoT to transact with each other directly and autonomously, driven by smart contracts. In the following section, a practical example will be provided on how to build a simple IoT device and connect it to the Ethereum blockchain. This IoT device is connected to the Ethereum blockchain and is used to open a door. In this case, the door lock is represented by an LED, when the appropriate amount of funds is sent by a user on the blockchain. This is a simple example and requires a more rigorously tested version to implement it in production. Nevertheless, it demonstrates how an IoT device can be connected to a blockchain. We will demonstrate how it can be controlled and responded to in response to certain events on an Ethereum blockchain. Implementing a blockchain-based IoT in practice. This example makes use of a Raspberry Pi device, which is a single board computer, SBC. The Raspberry Pi is an SBC developed as a low-cost computer to perform computer education, but it has also gained much more popularity as a tool of choice for building IoT platforms. A Raspberry Pi 3 Model B is shown in the following image. You may be able to use earlier models too, but those have not been tested. In the following section, an example will be discussed where a Raspberry Pi will be used as an IoT device connected to the Ethereum blockchain, and it will act in response to a smart contract invocation. Setting up Raspberry Pi. First, the Raspberry Pi needs to be set up. This can be done by using Noobs, which provides an easy method of installing Raspbian or any other operating system. Noobs is an abbreviation of New Out-of-Box Software. It is a user-friendly and easy-to-use operating system installation manager for the Raspberry Pi. For this example, Noobs has been used to install Raspbian. As such, the rest of the exercise assumes Raspbian is installed on the SD memory card of the Raspberry Pi. The command output in the following screenshot shows which architecture the operating system is running on. In this case, it is ARMv71. Therefore, the ARM-compatible binary for Geth will be downloaded. The platform can be confirmed by running the command uname-a in a terminal window in the Raspberry Pi Raspbian operating system. Once the Raspbian operating system has been installed, the next step is to download the appropriate Geth binary for the Raspberry Pi ARM platform. The download and installation steps are described in detail as follows. 1. First, download the Geth binary in Raspberry Pi. We used wget to download the Geth client images. 2. Unzip and extract this into a directory. The directory named geth-linux-arm7-1.5.6-2a609af5 will be created automatically with the tar command as shown here. This command will create a directory named geth-linux-arm7-1.5.6-2a609af5 and will extract the Geth binary and related files into that directory. The Geth binary can be copied into \usr\bin or the appropriate path on Raspbian to make it available for anywhere in the operating system. When the download is finished, the next step is to create the Genesis block. 3. The same Genesis block should be used that we created previously in Chapter 13, Ethereum Development Environment. The Genesis file can be copied from the other node on the network. This is shown in the following code segment. Alternatively, an entirely new Genesis block can be created. Elements of the Genesis file were explained in Chapter 13, Ethereum Development Environment, under the section entitled The Genesis File, which you can refer to as a refresher. 4. Once the genesis.json file has been copied onto the Raspberry Pi, the following command can be run to generate the Genesis block. It is important that the same Genesis block is used that was generated previously, otherwise the nodes will effectively be running on separate networks. This will show an output similar to the one shown in the following screenshot. 5. After Genesis block creation, we add peers to the network. This can be achieved by creating a list of nodes on our private network. In order to define the list, we create a file named static-nodes.json using any text editor and add the enode of the peer that Geth on the Raspberry Pi will connect to for synchronizing. 6. The enode URL can be obtained from the Geth JavaScript console by running the following command, which should be run on the peer to which Raspberry Pi is going to connect. This will show an output similar to the one shown in the following screenshot. 7. The static-nodes.json file should contain the enode value, as shown in the following screenshot. We can view the contents using the cat command. This command will produce the output shown here. After this step, further instructions presented in the following sections can be followed to connect Raspberry Pi to the other node on the private network. In this example, the Raspberry Pi will be connected to the network ID 786 that we created in Chapter 13, Ethereum Development Environment. The key is to use the same Genesis file created previously and different port numbers. Using the same Genesis file will ensure that clients connect to the same network in which the Genesis file originated. Different ports are not a strict requirement, however. If the two nodes are running under a private network and access from an environment external to the network is required, then a combination of DMZ, router, and port forwarding will be used. Therefore, it is recommended to use different TCP ports to allow port forwarding to work correctly. The -- identity switch, shown in the following section setting up the first node, which hasn't been introduced previously, allows for an identifying name to be specified for the node. Setting up the first node. First, the Geth client needs to be started on the first node using the following command. This will give an output similar to the following. Once this has been started up, it should be kept running and another Geth instance should be started from the Raspberry Pi node. Setting up the Raspberry Pi node. On Raspberry Pi, the following command is required to be run to start Geth and to sync it with other nodes. In this case, only one node. The following is the command. This should produce an output similar to the one shown in the following screenshot. When the output contains a row displaying block synchronization started, this means that the node has connected successfully to its peer. This can be further verified by running commands in the Geth console on both nodes, as shown in the following screenshot. The Geth client can be attached by simply running the following command on the Raspberry Pi, $Geth attach. This will open the JavaScript Geth console for interacting with the Geth node. We can use the admin.peers command to see the connected peers. Similarly, we can attach to the Geth instance by running the following command on the first node, $Geth attach ipc:/privatenet/geth.ipc. Once the console is available, admin.peers can be run to reveal the details about other connected nodes, as shown in the following screenshot. Once both nodes are up and running, further prerequisites can be installed to set up the experiment. Installation of Node.js and the relevant JavaScript libraries is required. Installing Node.js. The required libraries and dependencies are listed here. First, Node.js and NPM need to be updated on the Raspberry Pi Raspbian operating system. For this, the following steps can be followed. 1. Install Node.js on the Raspberry Pi using the following command: $curl-sl https://deb.nodesource.com/setup_7.x. This should display an output similar to the following. The output is quite large, therefore only the top part of the output is shown in the following screenshot. 2. Run the update via apt-get. $sudo apt-get install Node.js. Verification can be performed by running the following command to ensure that the correct versions of Node.js and NPM are installed, as shown in the following screenshot. It should be noted that these versions are not a necessity. Any of the latest versions of NPM and Node.js should work. However, the examples in this chapter make use of NPM 4.0.5 and Node v7.4.0 simply for demonstration, so it is recommended that you use the same versions in order to avoid any compatibility issues. 3. Install Ethereum Web3 NPM using the following command: $npm install web3 at 0.18.0. Web3 is required to enable JavaScript code to access the Ethereum blockchain. The output of the command will be similar to the one shown here. 4. Similarly, npm on-off can be installed, which is required to communicate with the Raspberry Pi and control GPIO. $npm install on-off. This will result in the following output indicating successful installation of on-off. In this section, we set up a private network with our Raspberry Pi and another node with Geth, Node.js, Web3, and the on-off library to run our example on. When all the prerequisites are installed, hardware setup can be performed. For this purpose, a simple circuit is built using a breadboard and a few electronic components. Hardware prerequisites. The hardware components are listed as follows: LED, a light-emitting diode. LED can be used as a visual indication for an event. Resistor. A 330 ohm component is required, which provides resistance to the passing current based on its rating. It is not necessary to understand the theory behind it for this experiment. Any standard electronics engineering text covers all these topics in detail. Breadboard. This provides a means of building an electronic circuit without requiring soldering. T-shaped cobbler. This is inserted on the breadboard as shown in the following image, and provides a labeled view of all general-purpose I/O GPIO pins for the Raspberry Pi. Ribbon cable connector. This is simply used to provide connectivity between the Raspberry Pi and the breadboard via GPIO. All these components are shown in the following figure. Building the electronic circuit. As shown in the following image, the positive leg, long leg of the LED is connected to pin number 21 of the breadboard, and the negative, short leg, is connected to the resistor, which is then connected to the ground, GND pin of the breadboard. Once the connections have been set up, the ribbon cable can be used to connect to the GPIO connector on the Raspberry Pi. Once the connections have been set up correctly and the Raspberry Pi has been updated with the appropriate libraries and Geth, the next step is to develop a simple smart contract that expects a value. If the value provided is not what it expects, it does not trigger an event. Otherwise, if the value passed matches the correct value, the event triggers, which can be read by the client JavaScript program running via Node.js. Of course, the Solidity contract can be very complicated and can also deal with the ether sent to it. If the amount of ether is equal to the required amount, then the event can trigger. However, in this example, the aim is to demonstrate the usage of smart contracts to trigger events that can then be read by JavaScript running on Node.js, which then in turn can trigger actions on IoT devices using various libraries. The smart contract source code is shown as follows. The online Solidity compiler Remix IDE can be used to run and test this contract. The Application Binary Interface ABI required for interacting with the contract is also available in the Remix IDE Solidity compiler section, as shown in the following screenshot. The following is the ABI of the contract. There are two methods by which the Raspberry Pi node can connect to the private blockchain via the Web3 interface. The first is where the Raspberry Pi device is running its own Geth client locally and maintains its ledger, as shown in the following diagram. Sometimes with resource-constrained devices, it is not possible to run a full Geth node or even a light node. In that case, the second method, which uses a Web3 provider via HTTP RPC server, can be used to connect to the appropriate RPC channel. The following diagram shows the high-level architecture of an IoT application where the Raspberry Pi does not run a Geth instance. Instead, it runs only the minimum software required to provide IoT application functionality to the IoT device. For blockchain-relevant operations, it connects to another blockchain node running on the network via HTTP RPC. There are obvious security concerns that arise from exposing RPC interfaces publicly. Therefore, it is recommended that this option is used only on private networks. If required to be used on public networks, appropriate security measures need to be put in place, such as allowing only the known IP addresses to connect to the Geth RPC interface. This can be achieved by a combination of disabling peer discovery mechanisms and HTTP RPC server listening interfaces. More information about this can be found using Geth help. The traditional network security measures such as firewalls, transport layer security, TLS, and certificates can also be used but have not been discussed in this example for brevity. Now, Truffle can be used to deploy the contract on the private network ID 786, to which at this point the Raspberry Pi is connected. Truffle deploy can be performed simply by using the following command. It is assumed that truffle init and other preliminaries discussed in Chapter 15 introducing Web3 have already been performed. $truffle migrate. This should produce an output similar to the following. Once the contract has been deployed correctly, JavaScript code can be developed that will connect to the blockchain via Web3. Listen for the events from the smart contract in the blockchain and turn the LED on via the Raspberry Pi. The JavaScript code required for this example is shown here. Simply write or copy and paste the code shown here into a file named index.js. Also, note the HTTP RPC server listening port on which Geth has been started on Raspberry Pi. By default, it is TCP port A545. Remember to change this according to your Raspberry Pi setup and Geth configuration. It is set to 9002 in the preceding example code because Geth running on Raspberry Pi is listening on 9002 in the example. If it's listening on a different port on your Raspberry Pi, then change it to that port. When Geth starts up, it shows which port it has HTTP endpoint listening on. This is also configurable with --RPC port in Geth by specifying the port number value as a parameter to the flag. This JavaScript code can be placed in a file on the Raspberry Pi, for example, index.js. It can be run by using the following command: $node index.js. This will start the program, which will run on node.js and listen for events from the smart contract. Once the program is running correctly, the smart contract can be invoked by using the Truffle console, as shown in the following screenshot. In this case, the getRent function is called with the parameter 10, which is the expected value. After the contract has been mined, room rented will be triggered, which will turn on the LED. In this example, it is a simple LED, but it can be any physical device, such as a room lock that can be controlled via an actuator. If all works well, the LED will be turned on as a result of the smart contract's function invocation, as shown in the following image. Also, on the node side, it will display an output similar to the one shown here. $node index.js LED on. As demonstrated in the preceding example, a private network of IoT devices can be built that runs a Geth client on each of the nodes, listens for events from smart contracts, and triggers an action accordingly. The example shown is simple by design but demonstrates the underlying principles of an Ethereum network that can be built using IoT devices along with smart contract-driven control of the physical devices. In the next few sections, other applications of the blockchain will be discussed, such as in government, finance, and health. Government. There are various applications of blockchain being researched currently that can support government functions and take the current model of e-government to the next level. First, in this section, some background for e-government will be provided, and then a few use cases such as e-voting, homeland security, border control, and electronic IDs, citizen ID cards, will be discussed. Government or electronic government is a paradigm where information and communication technology are used to deliver public services to citizens. The concept is not new and has been implemented in various countries around the world. But with blockchain, a new avenue of exploration has opened up. Many governments are researching the possibility of using blockchain technology for managing and delivering public services, including but not limited to identity cards, driving licenses, secure data sharing among various government departments, and contract management. Transparency, auditability, and integrity are attributes of blockchain that can go a long way in effectively managing various government functions. Border control. Automated border control systems have been in use for decades, now to thwart illegal entry into countries and prevent terrorism and human trafficking. Machine-readable travel documents, specifically biometric passports, have paved the way for automated border control. However, current systems are limited to a certain extent, and blockchain technology can provide solutions. A machine-readable travel document (MRTD) standard is defined in document ICAO 9303 by the International Civil Aviation Organization (ICAO) and has been implemented by many countries around the world. Each passport contains various security and identity attributes that can be used to identify the owner of the passport, and also circumvent attempts at tampering with these passports. These include biometric features such as retina scan, fingerprints, facial recognition, and standard ICAO specified features, including machine-readable zone (MRZ), and other text attributes that are visible on the first page of the passport. One key issue with current border control system is data sharing, whereby the systems are controlled by a single entity, and data is not readily shared among law enforcement agencies. This lack of ability to share data makes it challenging to track suspected travel documents or individuals. Another issue is related to the immediate implementation of blacklisting of a travel document. For example, when there is an immediate need to track and control suspected travel documents. Currently, there is no mechanism available to blacklist or revoke a suspicious passport immediately and broadcast it to the border control ports worldwide. Blockchain technology can provide a solution to this problem by maintaining a blacklist in a smart contract that can be updated as required. Any changes will be immediately visible to all agencies and border control points, thus enabling immediate control over the movement of a suspected travel document. It could be argued that traditional mechanisms like public key infrastructures, PKIs, and P2P networks can also be used for this purpose, but they do not provide the benefits that a blockchain can provide. With blockchain, the whole system can be simplified without the requirement of complex networks and PKI setups, which will also result in cost reduction. Moreover, blockchain-based systems will provide cryptographically guaranteed immutability, which helps with auditing and discourages any fraudulent activity. The full database of all travel documents may not be stored on the blockchain currently due to inherent storage limitations, but a back-end distributed database such as BigchainDB, IPFS, or Swarm can be used for that purpose. In this case, a hash of the travel document with the biometric ID of an individual can be stored in a simple smart contract, and a hash of the document can then be used to refer to the detailed data available on the distributed file system, such as IPFS. This way, when a travel document is blacklisted anywhere on the network, that information will be available immediately with the cryptographic guarantee of its authenticity and integrity throughout the distributed ledger. This functionality can also provide adequate support in anti-terrorism activities, thus playing a vital role in the homeland security function of a government. A simple contract in Solidity can have an array defined for storing identities and associated biometric records. This array can be used to store the identifying information about a passport. The identity can be a hash of MRZ of the passport or travel document concatenated with the biometric record from the RFID chip. A simple Boolean field can be used to identify blacklisted passports. Once this initial check passes, further detailed biometric verification can be performed by traditional systems. Eventually, when a decision is made regarding the entry of the passport holder, that decision can be propagated back to the blockchain, thus enabling all participants on the network to immediately share the outcome of the decision. A high-level approach to building a blockchain-based border control system can be visualized as shown in the following diagram. In this scenario, the passport is presented for scanning to an RFID and page scanner, which reads the data page and extracts machine-readable information along with a hash of the biometric data stored in the RFID chip. At this stage, a live photo and retina scan of the passport holder is also taken. This information is then passed on to the blockchain, where a smart contract is responsible for verifying the legitimacy of the travel document by first checking its list of blacklisted passports, and then requesting more data from the backend IPFS database for comparison. Note that the biometric data, such as a photo or retina scan, is not stored on the blockchain. Instead, only a reference to this data in the backend, IPFS or BigchainDB, is stored in the blockchain. If the data from the presented passport matches with what is held in the IPFS as files or in BigchainDB, and also passes the smart contract logical check, then the border gate can be opened. After verification, this information is propagated throughout the blockchain and is instantly available to all participants on the border control blockchain. These participants can be a worldwide consortium of homeland security departments of various nations. Voting. Voting in any government is a key function and allows citizens to participate in the democratic election process. While voting has evolved into a much more mature and secure process, it still has limitations that need to be addressed to achieve a desired level of maturity. Usually the limitations in current voting systems revolve around fraud, weaknesses in operational processes, and especially transparency. Over the years, secure voting machines have been built that make use of specialized voting machines that promise security and privacy, but they still have vulnerabilities that could be exploited to subvert the security mechanisms of those machines. These vulnerabilities can lead to serious implications for the whole voting process and can result in mistrust in the government by the public. Blockchain-based voting systems can resolve these issues by introducing end-to-end security and transparency in the process. Security is provided in the form of integrity and authenticity of votes by using public key cryptography, which comes as a standard in a blockchain. Moreover, immutability guaranteed by blockchain ensures that votes cast once cannot be cast again. This can be achieved through a combination of biometric features and a smart contract maintaining a list of votes already cast. For example, a smart contract can maintain a list of already cast votes with the biometric ID, for example, a fingerprint, and can use that to detect and prevent double casting. Secondly, zero-knowledge proofs, ZKPs, can also be used on the blockchain to protect voters' privacy. With ZKP, a voter can remain anonymous by hiding their identities, and the vote itself can be kept confidential. Citizen identification, ID cards. Electronic IDs or national ID cards are issued by various countries around the world at present. These cards are secure and possess many security features that thwart duplication or tampering attempts. However, with the advent of blockchain technology, several improvements can be made to this process. Digital identity is not only limited to just government-issued ID cards. It is a concept that applies to online social networks and forums too. There can be multiple identities being used for different purposes. A blockchain-based online digital identity allows control over personal information sharing. Users can see who used their data and for what purpose, as well as control access to it. This is not possible with the current infrastructures, which are centrally controlled. The key benefit is that a single identity issued by the government can be used easily and in a transparent manner for multiple services via a single government blockchain. In this case, the blockchain serves as a platform where a government is providing various services, such as pensions, taxation, or benefits, and a single ID is being used to access all these services. Blockchain in this case provides a permanent record of every change and transaction made by a digital ID, thus ensuring integrity and transparency of the system. Also, citizens can notarize birth certificates, marriages, deeds, and many other documents on the blockchain tied with their digital ID as a proof of existence. Currently, there are successful implementations of identity schemes in various countries that work well, and there is an argument that perhaps blockchain is not required in identity management systems, although there are several benefits such as privacy and controlling the use of identity information. Due to the current immaturity of blockchain technology, perhaps it is not ready for use in real-world identity systems. However, research is being carried out by various governments to explore the use of blockchain for identity management. Moreover, laws such as the right to be forgotten can be quite difficult to incorporate into blockchain due to their immutable nature. Other government functions where blockchain technology can be implemented to improve cost and efficiency include the collection of taxes, benefits management and disbursement, land ownership record management, life event registration, marriages, births, motor vehicle registration, and licenses. This is not an exhaustive list, and over time many functions and processes of a government can be adapted to a blockchain-based model. The key benefits of blockchain, such as immutability, transparency, and decentralization, can help to bring improvements to most of the traditional government systems. Now, let's see how the health industry can benefit from blockchain technology. Health. The health industry has also been identified as another major industry that can benefit by adapting blockchain technology. Blockchain can provide an immutable, auditable, and transparent system that traditional P2P networks cannot. Also, blockchain provides a simpler, more cost-effective infrastructure compared to traditional, complex PKI networks. In healthcare, major issues such as privacy compromises, data breaches, high costs, and fraud can arise from a lack of interoperability, overly complex processes, transparency, auditability, and control. Another burning issue is counterfeit medicines, especially in developing countries. This is a major cause of concern. With the adaptability of blockchain in the health sector, several benefits can be realized, including cost savings, increased trust, the faster processing of claims, high availability,
no operational errors due to complexity in the operational procedures, and preventing the distribution of counterfeit medicines. From another angle, blockchains that are providing a digital currency as an incentive for mining can be used to provide processing power to solve scientific problems. This helps to find cures for certain diseases. Examples include Folding Coin, which rewards its miners with FLDC tokens for sharing their computer's processing power for solving scientific problems that require unusually large calculations. Another similar project is called CureCoin, which is available at curecoin.net. It is yet to be seen how successful these projects will be in achieving their goals, but the idea is very promising. In the next section, we'll explore one of the most talked about and anticipated industries that can benefit from blockchain technology: finance. Finance. Blockchain has many potential applications in the finance industry. Blockchain in finance is currently the hottest topic in the industry, and major banks and financial organizations are researching to find ways to adopt blockchain technology, primarily due to its highly desired potential to cost save. These applications include, but are not limited to, insurance, post-trade settlements, financial crime prevention, and payments. Insurance. In the insurance industry, blockchain technology can help to stop fraudulent claims, increase the speed of claim processing, and enable transparency. Imagine a shared ledger between all insurers that can provide a quick and efficient mechanism for handling intercompany claims. Also, with the convergence of IoT and blockchain, an ecosystem of smart devices can be imagined, where all these things can negotiate and manage their insurance policies, which are controlled by smart contracts on the blockchain. Blockchain can reduce the overall cost and effort required to process claims. Claims can be automatically verified and paid via smart contracts and the associated identity of the insurance policyholder. For example, a smart contract with the help of an Oracle and possibly IoT can make sure that when the accident occurred, it can record related telemetry data and based on this information, release payment. It can also withhold payment if the smart contract, after evaluating conditions of payment, concludes that payment should not be released. For example, in a scenario where an authorized workshop did not repair the vehicle or was used outside a designated area, and so on and so forth. There can be many conditions that a smart contract can evaluate to process claims, and the choice of these rules depends on the insurer. But the general idea is that smart contracts in combination with IoT and oracles can automate the entire vehicle insurance industry. Several startups such as Dynamis have proposed smart contract-based P2P insurance platforms that run on the Ethereum blockchain. This was initially proposed to be used for unemployment insurance and does not require underwriters in the model. Post-trade settlement. This is the most sought-after application of blockchain technology. Currently, many financial institutions are exploring the possibility of using blockchain technology to simplify, automate, and speed up the costly and time-consuming post-trade settlement process. To understand the problem better, the trade life cycle will be described briefly. A trade life cycle contains 3 steps: execution, clearing, and settlement. Execution is concerned with the commitment of trading between 2 parties and can be entered into the system via front office, order management terminals, or exchanges. Clearing is the next step, whereby the trade is matched between the seller and buyer based on certain attributes such as price and quantity. At this stage, accounts that are involved in payment are also identified. Finally, the settlement is where, eventually, security is exchanged for payment between the buyer and seller. In the traditional trade lifecycle model, a central clearinghouse is required to facilitate trading between parties, which bears the credit risk of both parties. The current scheme is somewhat complicated, whereby a seller and buyer have to take a complicated route to trade with each other. This comprises various firms, brokers, clearinghouses, and custodians, but with blockchain, a single distributed ledger with appropriate smart contracts can simplify this whole process and can enable buyers and sellers to talk directly to each other. Notably, the post-trade settlement process usually takes 2 to 3 days and has a dependency on central clearinghouses and reconciliation systems. With the shared ledger approach, all participants on the blockchain can immediately see a single version of truth regarding the state of the trade. Moreover, P2P settlement is possible, which results in the reduction of complexity, cost, risk, and the time it takes to settle the trade. Finally, intermediaries can be eliminated by making use of the appropriate smart contracts on the blockchain. Also, regulators can view the blockchain for auditing and regulatory requirements. Financial crime prevention. Know Your Customer, KYC, and anti-money laundering, AML, are the key enablers for the prevention of financial crime. In the case of KYC, currently each institution maintains their own copy of customer data and performs verification via centralized data providers. This can be a time-consuming process and can result in delays in onboarding a new client. Blockchain can provide a solution to this problem by securely sharing a distributed ledger between all financial institutions that contain verified and true identities of customers. This distributed ledger can only be updated by consensus between the participants, thus providing transparency and auditability. This can not only reduce costs but also enable regulatory and compliance requirements to be satisfied in a better and consistent manner. In the case of AML, due to the immutable, shared, and transparent nature of blockchain, regulators can easily be granted access to a private blockchain where they can fetch data for relevant regulatory reporting. This will also result in reducing complexity and costs related to the current regulatory reporting paradigm. This is where data is fetched from various legacy and disparate systems and then aggregated and formatted together for reporting purposes. Blockchain can provide a single shared view of all financial transactions in the system that are cryptographically secure, authentic, and auditable, thus reducing the costs and complexity associated with the currently employed regulatory reporting methods. Payments. A payment is a transfer of money or its equivalent from one party, the payer, to another, the payee, in exchange for services, goods, or for fulfilling a contract. Payments are usually made in the form of cash, bank transfers, credit cards, and checks. There are various electronic payment systems in use, such as BACS Payment Schemes Limited, BACS, and the Clearinghouse Automated Payment System, CHAPS. All of these systems are, however, centralized and governed by traditional finance service industry codes and practices. These systems work adequately, but with the advent of blockchain, the potential of technology has arisen to address some of these limitations. Some of the key advantages that blockchain technology can bring to payments are listed as follows. Decentralization. Decentralization means that there is no requirement of a trusted third party to process payments. Payments can be made directly between parties without requiring any intermediary. This can result in reduced costs and faster direct payments between parties. Faster settlement. Settlement can be much quicker compared to the traditional network due to the active presence of all parties on the network. Payment data can be shared and seen by all parties at the same time, and due to this, settlement becomes quicker and more comfortable. Moreover, there is no requirement of running lengthy reconciliation processes because the data is all there on the blockchain, shared between all parties and readily available, which removes the requirement of the lengthy reconciliation process. Better resilience. With the payment system running on a blockchain with potentially thousands of nodes around the world, the network becomes naturally resilient. It could also be argued that with blockchain payments, there is no downtime because blockchain does not rely on traditional disaster recovery (DR) practices and is also better protected against malicious and denial of service attacks. With all these advantages, it is easy to see how the payments industry can benefit from blockchain technology. There is also another branch of payments that deals with international or cross-border payments, and comes with its own challenges. We'll discuss this next. Cross-border payments. In traditional finance, cross-border payment is a complex process that can take days to process and involves multiple intermediaries. Current mechanisms suffer from delays incurred by multiple intermediaries, enforcement of regulations, differences in terms of regulations between different jurisdictions. The list goes on. All of these issues can be addressed by utilizing blockchain technology. The most significant advantage is decentralization, where, due to the lack of requirement of intermediaries, payments can be made directly between businesses or individuals. Also, due to P2P connectivity, the whole process becomes a lot faster, almost immediate, in fact, which results in more productivity and business agility. Peer-to-peer loans. Blockchain also enables P2P loans, where lenders and borrowers can deal with each other directly instead of relying on a third party. Currently, in the decentralized finance (DeFi) landscape, there is a large percentage of lending apps that deal with the lending and borrowing of crypto tokens. In this section, we covered some common use cases of blockchain in the finance industry. Next, we'll discuss media, another use case where blockchain can provide a cheaper, fair, and transparent media ecosystem. Media. Critical issues in the media industry revolve around content distribution, rights management, and royalty payments to artists. For example, digital music can be copied many times without any restrictions, and any attempts to apply copy protection have been hacked in some way or other. There is no control over the distribution of the content that a musician or songwriter produces. It can be copied as many times as needed without any restriction, and consequently has an impact on the royalty payments. Also, payments are not always guaranteed and are based on traditional airtime figures. All these issues revolving around copy protection and royalty payments can be resolved by connecting consumers, artists, and all players in the industry, allowing transparency and control over the process. Blockchain can provide a network where digital music is cryptographically guaranteed to be owned only by the consumers who pay for it. This payment mechanism is controlled by a smart contract instead of a centralized media agency or authority. The payments will be automatically made based on the logic embedded within the smart contract and the number of downloads. Moreover, illegal copying of digital music files can be stopped altogether because everything is recorded and owned immutably in a transparent manner on the blockchain. A music file, for example, can be stored with owner information and a timestamp that can be traced throughout the blockchain network. Furthermore, the consumers who own a legal copy of some content are cryptographically tied to the content they have, and it cannot be moved to another owner unless permissioned by the owner. Copyrights and transfers can be managed easily via blockchain once all digital content is immutably recorded on the blockchain. Smart contracts can then control the distribution and payment to all concerned parties. Summary. There are many applications of blockchain technology, and as discussed in this chapter, they can be implemented in various industries to bring about solutions to existing problems. In this chapter, 5 main industries that can benefit from blockchain have been discussed. First, IoT was discussed, which is another revolutionary technology in its own right. By combining it with blockchain, several fundamental limitations can be addressed, which brings about tremendous benefits to the IoT industry. More focus has been given to IoT in this chapter as it is the most prominent and most ready candidate for adopting blockchain technology. Moreover, applications in the government sector were discussed, whereby various government processes such as Homeland Security, identification cards, and benefit disbursements can be made transparent, secure, and more robust. Furthermore, issues in the finance sector were discussed, along with possible solutions that blockchain technology could provide. Although the finance sector is exploring the possibilities of using blockchain with high energy and enthusiasm, it is still far away from production-ready, blockchain-based systems. Finally, some aspects of the health sector and music industry were also discussed. All these use cases and much more in the industry stand on pillars provided by core attributes of blockchain technology, such as decentralization, transparency, reliability, and security. However, certain challenges need to be addressed before blockchain technology can be adopted fully. These will be discussed in the next chapter. Chapter 20: Enterprise Blockchain. In this chapter, we'll investigate enterprise blockchains. What is the standard architecture of enterprise blockchains? Why they are required? We will answer these questions and will also try to answer the big question of why current public blockchains are not necessarily a suitable choice for enterprise use cases. We will also introduce several enterprise blockchain platforms, including Quorum and Corda. Along the way, we'll cover the following topics: enterprise solutions and blockchain, limiting factors, requirements, enterprise blockchain versus public blockchain, use cases of enterprise blockchains, enterprise blockchain architecture, designing enterprise blockchain solutions, blockchain in the cloud, currently available enterprise blockchains, enterprise blockchain challenges, Corda, Quorum, setting up Quorum with IBFT, other Quorum projects. We discuss several different blockchain types in Chapter 1, Blockchain 101, including permissioned, public, private, and consortium blockchains. Enterprise blockchains are a permission consortium chain type that primarily tackle enterprise requirements. Permission doesn't mean private. Permission blockchains can also be public and allow access only to known participants. Enterprise blockchains are usually private and permissioned, and are run between consortium members. While public blockchains provide integrity, consistency, immutability, and security guarantees, they lack certain features which makes them less suitable for enterprise usage. We'll discuss these limitations in detail shortly. First, we'll look into what enterprise solutions are and how blockchain can fit into an enterprise. Secondly, we'll see what questions should be answered before introducing an enterprise blockchain solution to a business. Enterprise solutions and blockchain. Enterprise solutions integrate different fragments of a business and enable it to achieve its goals by providing business-critical information to the stakeholders. Therefore, an enterprise blockchain solution should be able to achieve this outcome. Here, we'll consider the question, does blockchain fit this definition and help achieve enterprise business goals? If a blockchain solution can integrate different facets of a business and enable it to achieve its goals, then clearly it is an enterprise solution that brings real business value. In order to find out if a blockchain is suitable for an enterprise or not, we can ask some questions. Some of these questions are listed as follows. How can business enterprise processes be improved using blockchain technology? Do I really need an enterprise blockchain? For this, we can ask some questions to rationalize whether we need an enterprise blockchain solution or not. Does my use case need shared data between participants? Have participants from other organizations that are not necessarily trustworthy and have conflicting interests? Need strict auditing? A blockchain can provide this, as it is an immutable and tamper-proof chain of records that can provide a definite audit trail of activities performed on the chain. Enterprise system. Need to ensure the confidentiality of transactions? Need to ensure the anonymity of participants? Need controlled but transparent updates to the ledger? Not need a single trusted authority. Instead, the decisions on the network updates to the ledger should be consortium member-driven and agreed between members. If the answer to any of the preceding questions is yes, then using an enterprise blockchain solution could be a good option. Otherwise, a traditional database might give a better alternative. In addition to the questions mentioned here, when proposing an enterprise blockchain solution, we also need to answer some other questions from a business perspective that help establish the overall vision and strategy of the implementation of the blockchain solution. What is the overall objective of the proposed blockchain solution? Does it align with the business goals of the enterprise? Is it a proof of concept (POC) project intended just to demonstrate an idea, or a production project with real business deliverables? Where would it be deployed? Cloud or local hosting? Who will manage the blockchain solution once it is deployed? Risk management considerations. Does the solution follow any established guidelines for risk management? For example, NIST 800-37 is a risk management framework that provides a process used to manage security and privacy risk for IT systems and organizations. Are there any other projects that this organization may have implemented already using enterprise blockchain? Can we learn from previous experiences and leverage some of the resources and best practices that may have been developed previously? These questions should be and are usually asked when developing any other enterprise solution. But in relation to blockchain, these questions become even more critical due to the nascent and immature nature of enterprise blockchain technology. A clear definition of the objectives, along with clear alignment with business requirements, will result in an implementation that meets business goals. Now the question arises regarding how blockchain solutions can be developed that can bring real business value. We'll learn later in this chapter how enterprise blockchain solutions can be designed using established architecture frameworks. So, in summary, after answering the aforementioned questions even informally and then engaging in a formal exercise of designing an enterprise blockchain solution using an enterprise framework, we can answer the question regarding whether a proposed blockchain solution is an enterprise solution that meets business objectives. We'll cover designing enterprise blockchain solutions later in this chapter. Next, we'll envisage some success factors that can help enterprise blockchains to become successful and adopted in the enterprise. Success factors. There are some business-oriented factors that should be addressed for a successful enterprise blockchain solution. Of the utmost importance is the requirement that the blockchain solution should bring some economic value and help to achieve real business goals. Moreover, enterprise solutions should be aligned with business goals. The primary value of enterprise blockchains is in the property of being a shareable, replicable, permissioned ledger between organizations that immediately results in cost reduction by eliminating the need for data exchange. In doing so, we also eliminate the need for infrastructure and tools to support such exchanges. Also, due to the security, immutability, and auditing provided as inherent features of a blockchain, there is no need to invest separately for these requirements. Blockchain solutions that integrate easily, seamlessly with existing systems provide better value because already mature legacy systems, at least at this stage, provide a mechanism to connect with the blockchain, read its data, and save it in a known format that the enterprise is already familiar with. Moreover, just a blockchain network on its own is not entirely useful in enterprises if it is not integrated with existing back-office systems such as Enterprise Resource Planning, ERP, back-end databases, record reconciliation systems, or other organization reporting tools. An enterprise blockchain solution should be seen as a complete end-to-end enterprise solution as part of the larger enterprise architecture, instead of only a siloed blockchain network. We'll explore this topic later in this chapter under the Designing Enterprise Blockchain Solutions section. Enterprise-grade governance, control, and security are also desirable features from a business perspective as they allow business stakeholders to apply already established organization rules and policies to the blockchain. This can also help to achieve regulatory and compliance requirements. Now, the following question arises. With the availability of many different public blockchain platforms, why has the adoption of blockchain technology in enterprises still not been fully achieved? The reason is that there are several factors that make public blockchains unsuitable for enterprise use cases. In the next section, we'll answer this question and explore why public blockchains are not quite suitable for enterprise use cases. Limiting factors. We discuss several benefits of blockchain technology in general in Chapter 1, Blockchain 101. While all those benefits are attainable using public blockchains, several features are lacking in public blockchains, which makes them unsuitable for use in enterprise use cases. The interest in enterprise blockchain arises from these limitations in public blockchains along with specific requirements in any business. We'll describe some of the most common concerns next. Slow performance. Public blockchains are slow and can process only a few transactions per second. Bitcoin processes 3 to 4 transactions per second, while Ethereum processes around 14. This low transaction rate is not suitable for business that usually require high transaction speed. For example, card payment businesses typically need to process thousands of transactions per second. Lack of access governance. Public blockchains are available for anyone to join, which makes it easier for investors and cryptocurrency enthusiasts to join and helps with the network effect. However, in an enterprise, all participants must be known so that everyone knows who they are dealing with. This lack of an identification and access control mechanism makes public blockchains rather unsuitable for businesses. Lack of privacy. Public blockchains are inherently transparent and everything on the ledger is visible to everyone. This means anyone can easily view transaction details and participants involved in a transaction. Probabilistic consensus. Public blockchains usually use a proof-of-work (POW) type of consensus mechanism, which is inherently a probabilistic protocol that provides probabilistic finality. Even though the confirmations mechanism, as discussed in Chapter 6, Introducing Bitcoin, does give a certain level of confidence that a transaction is irrevocable, it is still possible that the chain may fork and transactions can be lost. This issue is particularly a concern for businesses where once a transaction commits, it is deemed final. Imagine receiving a property ownership document on a chain from someone only to discover later that the blockchain has forked and that you are no longer the owner of the property. To address this limitation, enterprise blockchains use deterministic consensus algorithms, which provide immediate finality. Transaction fees. In Ethereum or other similar blockchains, the transaction fee is charged in the native cryptocurrency for each transaction execution. While this mechanism provides incentives for miners and protects against spam, there is no requirement of such an arrangement in enterprise blockchains. If an organization were to use public blockchains for their business transactions, then they'd need cryptocurrency in reserve to pay for operations on the blockchain. This extra cost might be undesirable for some businesses. While the concerns mentioned here are considered limitations in public blockchains based on these concerns and limitations, we can derive and define several requirements or features of a blockchain that will enable it to become an enterprise blockchain. In other words, the limitations in public blockchains can be seen as requirements of enterprise blockchains. The next section talks about several features that a blockchain should possess to become suitable for enterprises. Requirements. In addition to integrity and consistency, which are also provided by public blockchains, there are several other requirements specifically for enterprise blockchains that make them suitable for enterprise use cases. In some cases, some requirements become even stricter in enterprise blockchains compared to public blockchains. For example, in public blockchains, eventual consistency is acceptable. However, in enterprise blockchains, the moment a transaction is committed, it should immediately finalize and irrevocably become part of the global record state. Thus, we'll begin by briefly defining integrity and consistency before introducing specific requirements for enterprise blockchains. Integrity. This attribute of a blockchain is provided by the use of hash functions and digital signatures and plays a vital role in the overall security of the blockchain. Hash functions allow us to check for any data modifications, whereas digital signatures ensure that the messages that originated from a sender have not been altered. Consistency. This attribute of a blockchain ensures that all honest nodes agree on the same sequence of blocks. To achieve this, various mechanisms are used, such as POW or Byzantine fault tolerance (BFT) consensus protocols. Now we'll introduce 3 fundamental requirements that should be met for a blockchain to become suitable for enterprises. These requirements are privacy, performance, and access governance. Privacy. Privacy is of paramount importance in enterprise blockchains. Privacy has 2 facets. First, confidentiality, and second, anonymity. Confidentiality. Confidentiality is a fundamental requirement in an enterprise. It is anticipated that in enterprise blockchains, all transactions hide their payloads so that the amount of transactions is not revealed to anyone who is not privy to the transaction. Types of private transaction. Private transactions can be defined as transactions that meet the privacy requirements of an enterprise use case. There are 2 types of private transactions as defined by Enterprise Ethereum Alliance, EEA. Restricted private transactions. This type of private transaction is transmitted only to those parties on the blockchain network who are privy to the transaction. Unrestricted private transactions. Under the unrestricted private transaction paradigm, private transactions are transmitted to all participants on the network, regardless of whether they are party to the transaction or not. The payload is still encrypted and confidential, but the transaction itself is broadcasted to the entire network. There are many approaches to achieving privacy in enterprise blockchains and blockchain in general. These methods range from an off-chain mechanism like privacy managers used in Quorum and some other enterprise chains, to utilizing zero-knowledge proofs, ZKPs, trusted hardware, and secure multi-party computation, SMPC. We'll cover some of these techniques in the next chapter, Chapter 21, Scalability and Other Challenges. But in this chapter, we will mainly focus on privacy manager-based privacy, where an off-chain component is used to provide privacy services. We will discuss the privacy manager-based approach in the Quorum section later in this chapter. Anonymity. Anonymity in enterprise blockchains might not seem a strict requirement at first, because all participants are known and identified. However, it is necessary for scenarios with some competing participants and conducting business on-chain. It could be essential, for example, that in a scenario where parties X and Y are transacting together, party Z doesn't find out which parties are transacting together. Even though the transaction values are not visible, it can still reveal details about the business that the 2 parties might be doing. If that information is available publicly, then other parties on the consortium chain will gain market intelligence and may try to influence that process via marketing or other methods. Performance. Due to the high-speed requirements of business, enterprise blockchains must be able to process transactions at a high rate. Scalability, speed. Performance has 2 facets, scalability and speed. Speed deals with how many transactions can be processed in a given amount of time. It deals with the ability of a system to handle a large volume of transactions at an acceptable speed. On the other hand, we have the number of participants in a system. Public blockchain can support a large number of users. This is especially true in cryptocurrency blockchains such as Bitcoin and Ethereum. This is possible due to the POW or proof-of-stake (POS) algorithms for consensus used in these public blockchains. However, in enterprise blockchains, a different class of consensus algorithms, most commonly BFT, are used, which do not work well with a large number of nodes. This results in limiting the number of users on a consortium chain. Here we have to consider a trade-off. Ideally, an enterprise blockchain should be able to perform well with a large number of users. However, with the trade-off, enterprise blockchains should be able to process transactions at a high rate. This is what most enterprise blockchains focus on since, in many use cases, the number of nodes is not that high, and speed can be prioritized over scalability. In public blockchains, sometimes network congestion caused by high volumes of traffic can cause performance issues and can increase the transaction processing times. This is detrimental to enterprise dApps, which need faster transaction processing and response times. Network congestion also results in increased gas prices, which can also be a concern for businesses from a cost perspective. Access governance. From another angle, being a permissioned blockchain, enterprise-grade access control in the form of either a new mechanism on the chain or control driven by an enterprise SSO already in place is a fundamental requirement in enterprise blockchains. As all participants must be identifiable on a consortium chain, it is essential to build an access control mechanism that facilitates that process. This feature can be achieved by using enterprise-grade access control mechanisms such as Role-Based Access Control, RBAC. The access control mechanism also can address Know Your Customer requirements. In addition to privacy, performance, and access governance, which are usually identified as three fundamental requirements of enterprise blockchains, there are also some other requirements that are highly desirable but can be considered somewhat optional, as they are more use case dependent. We'll describe these next. Further requirements. In this section, we'll present some further requirements that are very useful and can increase the suitability, efficacy of enterprise blockchain solutions. We'll discuss these requirements as follows. Compliance. A common concern is compliance. Public blockchains are not suitable for enterprise use cases due to strict regulatory and law requirements in almost all sectors such as finance, health, and government. Compliance challenges mainly include regulatory compliance, standards compliance, data sovereignty, and liability concerns. We'll define these briefly next. Compliance with standards and regulations. Often in enterprise use cases, compliance with a technical standard or laws is required. For example, compliance with GDPR is mandatory in the European Union and the European Economic Area. Another example is compliance with Financial Conduct Authority (FCA) regulations in the UK. Moreover, it might be necessary in a use case to comply with technical standards such as cryptography standards published by NIST. Data sovereignty. Data sovereignty is a broad topic that mainly subjects data to the laws of the country in which it is located. For example, under GDPR, transferring personal data outside the EU is subject to adequacy decisions, Article 45, and the appropriate safeguards, Article 46. As public blockchains are borderless and geographically dispersed systems, compliance with such regulations can be challenging. Liability. In traditional business and IT systems, legal responsibility often lies with the party who provides a specific service. For example, a cloud service provider being responsible for handling data in accordance with local laws and regulations. In a decentralized public blockchain, the data is on a public blockchain, and it therefore becomes challenging to keep a single party responsible for data management or providing services. In case of malicious incidents, again, it is not possible to hold any single party responsible. This limitation poses a significant challenge in enterprise settings where, usually, a responsible party is in control of service provision and is held accountable. From another angle, we know that in traditional systems, in case of any problems, a legal system can help. However, in a decentralized blockchain, it can become quite challenging to blame any single party for their actions. Therefore, in enterprise blockchains, the ability to comply with regulations and law becomes a very sought-after attribute. Interoperable. As the enterprise blockchain ecosystem evolves, the need to be able to exchange data between the disparate enterprise and public blockchains also arises. Lack of standardization also alleviates this problem. However, standardization efforts are underway, such as EEA, discussed in the Enterprise Blockchain Challenges section. There are also interoperability solutions being developed and available for blockchains that allow interoperability between chains, such as Ion, Polkadot, and Interledger. We will discuss interoperability further in Chapter 21, Scalability and Other Challenges. Integration. No enterprise blockchain is an isolated end-to-end solution. It has to integrate with existing enterprise systems or other off-chain systems that are part of the whole enterprise solution to fulfill business goals. Therefore, enterprise blockchains must provide interfaces for integration. This can be as simple as providing RPC endpoints, or as complex as building blockchain-specific connectors and plugins to integrate with Enterprise Service Bus or other legacy systems. More on this in the Enterprise Blockchain Architecture section. Integration with security devices such as hardware security modules, HSMs, is also quite desirable for many enterprise use cases where strict security is required, or due to regulatory or compliance requirements. Ease of use. Usually, enterprise systems are easy to deploy and use. Deployment in enterprise is easy and quick, and often relies on mature frameworks and tools such as Ansible and other proprietary tools. But this is not the case with blockchain. Deployment of enterprise systems is a well-studied, understood, and mature area. With enterprise orchestration tools and established techniques over the years, enterprise deployment has become easy. However, blockchains are not as easy to deploy as other enterprise systems. With the availability of blockchain as a service, BaaS, and deployment automation tools, this is changing. However, there is still some work that needs to be done. Monitoring. Monitoring using visualization tools plays a vital role in any enterprise solution. Without the ability to monitor and visualize a system, it is almost impossible to ensure the health of the enterprise system. It is also a desirable feature in enterprise blockchain solutions to be able to visualize the blockchain network. Monitoring a blockchain allows an administrator to keep an eye on the network's health and operations. It allows an administrator to monitor and respond to the events of interest, such as a node going down, communication link slowness, a node being unable to sync with the blockchain, and many other scenarios. Secure off-chain computation. In some scenarios, it is desirable to be able to offload some intensive computation to off-chain systems. For example, if there is a requirement to do some computation that requires high-performance computing, HPC resources. This somewhat overlaps with integration, but it's mentioned here separately because of specific security requirements that the off-chain computations must be provably correct with integrity and authenticity guarantees. Better tools. Usually in enterprise systems, there are many supporting tools and utilities packaged with the main product to operate the software. For example, these include administration tools, deployment tools, developer utilities, visualization tools, management tools, and end-user tools. Blockchain platforms with better tooling are much desirable because of better user support. Tools such as block explorers, user administration models, and the apps to manage smart contracts are quite useful. They are gradually becoming more mature as the whole blockchain ecosystem is growing. Now that we understand the features of enterprise blockchains, we will present a comparison between public and enterprise blockchains to help understand the main differences. Enterprise blockchain versus public blockchain. In this section, we'll provide a comparison between public and enterprise blockchains. Consider the table shown here, which assesses some points of comparison between the two blockchain types. This is not an exhaustive list. However, we'll touch on the most major points. The preceding table compares several key aspects of public and enterprise platforms. Next, we'll briefly consider some of the use cases of enterprise blockchains. Use cases of enterprise blockchains. Considering the preliminary considerations, limiting factors, and requirements which we've discussed so far of employing an enterprise blockchain in an organization, there are several clear use cases of enterprise blockchains. Some of these standout scenarios are listed as follows: payments, supply chain, IoT, insurance, healthcare. Evidently, enterprise blockchains have many use cases, including but not limited to payments, insurance, KYC, and monitoring supply chains. We introduce some of these use cases throughout this book, especially in Chapter 1, Blockchain 101, and some in Chapter 19, Blockchain Outside of Currencies. The use cases discussed in the latter chapter are also applicable to enterprise use cases, such as the Internet of Things scenario, which can be implemented in both public and private blockchains. We will cover some more use cases in the context of the latest developments in Chapter 22, Current Landscape and What's Next. In the next section, we'll describe enterprise blockchain architecture, which can help us communicate with stakeholders, promote early design decisions, serve as a reusable model for development, build shared understanding, and understand how the system is structured. Enterprise blockchain architecture. A typical enterprise blockchain architecture contains several elements. We saw a generic blockchain architecture in Chapter 1, Blockchain 101, and we can expand and modify that a little bit to transform it into an enterprise blockchain architecture that highlights the core requirements of an enterprise blockchain. These requirements are mostly driven by enterprise needs and use cases. We'll discuss each of these layers as follows. Network layer. The network layer is responsible for implementing network protocols such as peer-to-peer, P2P protocols used for information dissemination. Protocol layer. This is the actual ledger layer or blockchain where the core consensus, transaction management, and storage elements are implemented. Privacy layer. This layer is responsible for providing one of the core features of enterprise blockchain, privacy. There are a number of ways to achieve privacy, including off-chain privacy managers, zero-knowledge, and hardware-assisted privacy. Hardware-based privacy is usually supported using Trusted Execution Environments, TEEs. On the other hand, software or algorithmic privacy such as zero-knowledge proofs, ZKPs, are also quite common in enterprise blockchains. Governance layer. This layer is responsible for providing the enterprise-grade access control mechanism that controls the consortium network membership. This can either be controlled via on-chain permissioning system implemented in smart contracts as part of the software client, or can be integrated with existing off-chain enterprise permissioning systems such as Single Sign-On SSO or Active Directory AD. Integration layer. This layer provides APIs and a mechanism used to integrate with the legacy or existing back-office systems. This can be as simple as an RPC layer providing APIs over RPC, or can constitute built-in connectors and plugins for integrating with the enterprise service bus. The integration layer is responsible for ensuring integration with back-office, legacy, and existing off-chain systems. It is not part of the core protocol, but as part of the holistic view of the blockchain end-to-end solution. This layer is vital for delivering business results. While there are many techniques available, a commonly integration framework used in the enterprise environment is Apache Camel. This can also be used in blockchain solutions as it comes with the Ethereum Web3j library component. Let's provide a quick introduction to Apache Camel before we move on to other layers of the enterprise blockchain architecture. What is Apache Camel? Apache Camel is an open-source enterprise integration framework. It enables easy integration between various systems by utilizing enterprise integration patterns. It has hundreds of components for different systems such as databases, APIs, and MQs for easy integration between systems. For example, Web3 Connector Apache Camel Ethereum Connector is a feature-rich connector available in Apache Camel that enables integration between Ethereum chains and other systems. The Apache Camel Ethereum Connector works with Ethereum Geth nodes, Quorum, Parity, and Ganache. It supports JSON RPC API over HTTP and IPC with implementations for different blockchain operations such as NET, ETH, SHH, and so on. It has support for Ethereum filters and Ethereum name services, ENS, which can be explored further at ens.domains. It has support for JSON RPC API and is also a fully tested unit and integration solution. A generic high-level design using Apache Camel is shown in the following diagram. In the preceding diagram, we can see several enterprise blockchains connecting to Apache Camel using Apache Camel Ethereum connectors. Also, other systems connect to Apache Camel via their respective connectors. Apache Camel via connectors is responsible for integrating between all these systems. For example, it is entirely possible to use Apache Camel to take data from enterprise blockchains and store it in traditional SQL databases in the enterprise via suitable connectors. Now let's return to our discussion on the enterprise blockchain layers and introduce the application layer. Application layer. The application layer, as the name suggests, consists of dApps, smart contracts, tools, and other relevant software to support enterprise use cases. Security, performance, scalability, monitoring. On the left-hand side in the architecture diagram, figure 21.1, security, scalability, performance, and monitoring is shown. As each layer in the enterprise blockchain benefits from and indeed requires security, scalability, and performance, this layer is shown as encompassing all layers. Monitoring also plays a vital role in any enterprise solution. Without effective visualizations in such complex networks, it is almost impossible to keep track of everything. Therefore, this layer is shown as relevant to all enterprise blockchain layers. Now that we understand the architecture of enterprise blockchains in general, let's dive a little bit deeper into the mechanics of designing enterprise blockchain solutions. In the next section, we'll see which tools and frameworks we can use to build enterprise solutions. Designing enterprise blockchain solutions. An isolated blockchain in an enterprise is not sufficient enough to solve business problems. In addition to choosing a blockchain platform, there are some other factors to consider while introducing a blockchain in an enterprise. On top of the list of these factors is integration with the existing back-office and legacy systems. There are already established and mature frameworks like the Open Group Architecture Framework, TOGAF, Zachman Framework to facilitate enterprise architecture development. With the advent of enterprise blockchain technology, a question arises regarding whether we can leverage existing frameworks to address enterprise blockchain architectural needs. The answer is yes. In this section, we'll look at TOGAF and its architecture development method, ADM, and consider how blockchain solutions can benefit from the TOGAF framework. Without any architecture framework, it becomes quite challenging to have a holistic view of an enterprise and see how all business processes fit together. To address this challenge, we can use enterprise architecture frameworks. The purpose of enterprise architecture frameworks is to enable an organization to execute its business strategy effectively. It allows an organization to see an organization from different perspectives, including business, information, process, and technology, and make effective business decisions to achieve business goals. Let's now explore the popular enterprise architecture framework, TOGAF. TOGAF stands for the Open Group Architecture Framework. It is developed by the Open Group. It is a framework that enables organizations to systematically design, plan, and implement enterprise solutions in businesses. It has 4 architectural domains. Business architecture domain. This domain defines the business strategy, organization structure, business processes, and governance of the organization. Data architecture domain. This domain describes structures of an organization's data assets and relevant data management resources. Application architecture domain. This domain describes the enterprise applications, deployment blueprints, relationships, and interactions between applications, along with the relationships these applications have with business processes within the enterprise. Technology architecture domain. This domain defines the requirements of the technical architecture implementation of the enterprise applications. This includes the description of hardware, software, middleware, and network infrastructure required for implementation of the enterprise applications. Now, re-examining each domain with blockchain in mind, we can include blockchain at each layer and make decisions such as business requirements, the application architecture, logical and physical datasets, and finally, the infrastructure required for implementing the enterprise blockchain solution. After this basic introduction to TOGAF, let's dive a bit deeper to understand the method TOGAF uses to develop an IT architecture. Architecture Development Method. TOGAF ADM is a method for developing IT architecture that meets organizational business needs. It describes the process of moving from the foundational TOGAF architecture to an organization-specific architecture. This is an iterative process with continuous requirements management, which results in the development of an architecture that is specific to an organization and addresses specific needs. Once the architecture development is complete, the architecture can be published throughout the organization to develop a common understanding. The ADM is a tested and repeatable process for developing enterprise architectures. The process follows the following steps: establish architecture framework, develop architecture content, architecture governance, and implementation of architectures. The ADM has 9 phases, and each phase can be further divided into multiple steps. The ADM model is shown here. Now we'll describe each phase in more detail. Preliminary phase. This phase defines the groundwork of the architecture. It defines methodologies, architecture principles, the architecture scope, and assumptions about the architecture. It also defines the responsible parties for architecture delivery. From a blockchain perspective, we can define the overall blockchain strategy in this phase. Architecture vision. This phase validates business principles, goals, and the business strategy. It defines key business requirements as well as a high-level description of the business value expected from the architecture work. This phase also analyzes the impact of the new architecture on other processes. Business architecture. This phase proposes the baseline business architecture and develops a target business architecture, along with gap analysis. In a blockchain scenario, we can define the current state architecture and target state architecture at this stage. Information systems architecture. This phase defines the data architecture and application architecture. The data architecture includes building the baseline data architecture description, building data architecture models, doing impact analysis, review reference models, and viewpoints. Application architecture defines the baseline application architecture, builds application architecture models, and proposes applications. Both of these activities also perform gap analysis to validate the architecture being developed, as well as to find any shortfalls between the baseline architecture and the target architecture. Similar to the business architecture for an enterprise blockchain solution, we can define the current state architecture and target state architecture. Technology architecture. This phase is primarily concerned with reviewing the baseline business, data, and application architecture and building a baseline description of the current technology architecture in the enterprise. It also proposes the target technology architecture. In this phase, we can propose a target enterprise blockchain platform and the target solution. Opportunities and solutions. This phase performs evaluations and selects various proposed target architectures. Also, an implementation strategy and plan are proposed at this stage. We can apply this to blockchain in a similar fashion by evaluating or selecting the target architecture encompassing enterprise blockchain solutions. When evaluating blockchain solutions, a number of features that we presented earlier in the comparison between enterprise blockchain and public blockchain can also be used. For example, confidentiality, scalability, and finality. Migration planning. This phase creates and finalizes the comprehensive implementation plan for migrating to the target architecture from the current architecture. Implementation governance. This phase deals with the implementation of the target architecture. A strategy to govern the overall deployment and migration is developed here. We can also perform blockchain solution testing and devise a deployment strategy during this phase. Architecture change management. This phase is responsible for creating change management guidelines and procedures for the newly implemented target architecture. From a blockchain perspective, this phase can provide change management procedures for the newly implemented enterprise blockchain solution. With this, we've completed our introduction to TOGAF and explored the idea that enterprise blockchain solutions should be viewed through the lens of the enterprise architecture. The fundamental idea to understand here is that enterprise blockchain solutions are not merely a matter of quickly spinning up a network, creating a few smart contracts, creating a web frontend, and hoping that it will solve business problems. This setup may be useful as a POC or for an incredibly simple use case, but is certainly not an enterprise solution. We suggest that an enterprise blockchain solution must be looked through the lens of the enterprise architecture and regarded as a full-grade enterprise solution. This is so that we can effectively achieve the business goals intended to be solved by enterprise blockchain solutions. Next, let's explore how we could implement a blockchain business solution in an organization that has moved its operations to the cloud. Blockchain in the cloud. Cloud computing provides excellent benefits to enterprises, including efficiency, cost reduction, scalability, high availability, and security. Cloud computing delivers computing services such as infrastructure, servers, databases, and software over the internet. There are different types of cloud services available. A standard comparison is made between infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. A question arises here. Where does blockchain fit in? Blockchain as a service, or BaaS, is an extension of SaaS, whereby a blockchain platform is implemented in the cloud for an organization. The organization manages its applications on the blockchain, and the rest of the software management, infrastructure management, and other aspects such as security and operating systems are managed by the cloud provider. This means that the blockchain software and infrastructure are provided and maintained by the cloud provider. The customer or enterprise can focus on their business applications without worrying about other aspects of the infrastructure. The following is a comparison of different approaches. BaaS can be thought of as a SaaS, where the software is a blockchain. In this case, just like in SaaS, all services are externally managed. In other words, customers get a fully managed blockchain network on which they can build and manage their own dApps. Note that in the preceding diagram under the blockchain as a service column, applications have been replaced with blockchain as a differentiator between other cloud services and BaaS. Here, blockchain is the software, application provided and managed by the cloud service provider. Also, note that dApps have been added on top, which are managed by the enterprise internally. There are many BaaS providers. A few of them are listed as follows: AWS, Azure, Oracle, IBM. In the next section, we'll introduce some enterprise blockchain platforms. Currently available enterprise blockchains. As this is a very ripe area for research, and indeed the market is very active in this space, There have been several enterprises blockchain solutions developed and made available in the last few years. Notably, the year 2019 has been called the year of the enterprise blockchain, as many startups and enterprises focused on this area emerged. In this section, we will not cover all these platforms in detail, but will provide a brief introduction and links to more details on these chains. In this section, we will not cover all these platforms in detail, but will provide a brief introduction and links to more details on these chains. Corda. Corda is an open-source distributed ledger platform intended for businesses. It supports privacy and assured identity, making it scalable and interoperable. We'll explore Corda in more detail later in this chapter. Quorum. Quorum is an open-source enterprise blockchain platform. It aims to support enterprise business needs and allows a business to achieve business goals and unlock economic value by leveraging blockchain technology. It addresses crucial enterprise requirements including privacy, performance, and enterprise permissioning. We will also explore Quorum in greater detail later in this chapter. Fabric. Fabric is a Hyperledger project. It is an enterprise-grade distributed ledger that allows the development blockchain solutions with a modular architecture. It has a permissioned architecture, support modularization, pluggable consensus, and supports smart contracts. We discussed Hyperledger and other projects under it, such as Sawtooth, in detail in Chapter 17, Hyperledger. Autonity. Autonity is an Ethereum-based protocol. It enables permissioned, decentralized, and interoperable enterprise networks. More information can be found at autonity.io. In the next section, we'll provide a comparison of 3 leading enterprise distributed ledger platforms. Comparison of main platforms. In this section, we'll provide a comparison of leading enterprise blockchain platforms. We'll cover most of the desirable features of enterprise blockchains. This can be used as a reference for a quick comparison between these platforms. This comparison is based on the current implementations of these platforms available at the time of writing. However, as this is a very rapidly changing area, some features may change over time or new features might be added or improved. This comparison may also be used for the quick evaluation of these platforms and suitability for an enterprise use case. Now that we've examined some requirements, architectures, and use cases of enterprise blockchain, let's briefly describe some of the challenges that still face this technology in practice. Enterprise blockchain challenges. While enterprise blockchains have addressed core enterprise requirements, privacy, performance, and governance to some extent, there are still more challenges that need to be addressed. There is significant progress being made towards solving these issues. However, there is still a lot of work required to be done to adequately address these limitations. Some of these limitations are listed as follows. Interoperability. Blockchain solutions are built by different development teams with different target requirements. As a result, there are now many different types of blockchain, ranging from cryptocurrency public blockchains to application-specific blockchains, which are developed for a single business application. Data exchange between these chains is a crucial concern. While blockchain networks continue to grow independently, integration and interoperability between these chains remains a big concern. This problem also stems out from lack of standardization. If a standard specification is available, then all chains following that standard will become compatible automatically. However, what about those chains that are already deployed in production, including public chains? How do we achieve interoperability between them? Many business use cases have the requirement to get data from one organization to another or from one blockchain network to another. This is also true in the case of data exchange requirements between a public blockchain and consortium network. Lack of standardization. Lack of standardization is a commonly highlighted concern in enterprise blockchains and generally in the blockchain ecosystem. Traditional systems are mostly developed in line with standards defined by standards bodies such as NIST-FISMA standards for information security. Standards are also essential to achieving interoperability. Several initiatives have been taken to address the challenges mentioned here, and also to standardize enterprise blockchain platforms. A leading organization in this field is EEA. Saving a couple of lines here, deleted section heading and join two small sections. Please link up the sentence on the previous page with this one. In this field is EEA, a standards organization run by its members that aims to develop enterprise blockchain specifications. Compliance. There are various compliance requirements in almost all industries, especially finance, law, and health, where strict guidelines and rules have been mandated by regulatory authorities. Enterprise systems are expected to conform to these requirements. Blockchain initially started with a different focus of building an electronic cash system with egalitarian philosophy. Still, surely enterprises have a different vision and mindset. Some of the regulations include GDPR, SOX, and PCI, which define different requirements for an enterprise to conform to. Also, compliance with technical standards such as the NIST-FISMA standard for information security is necessary. There are also jurisdiction issues. A distributed network with geographically dispersed locations may require different legal requirements to be met in various jurisdictions. For example, a specific type of cryptography may be allowed by law in the US but not in Cuba. Business challenges. From a business perspective, cost, funding, and governance are some of the challenges that need to be met. If building and implementing an enterprise blockchain solution is prohibitively costly, then the business stakeholder might prefer traditional enterprise systems. Also, from an operational perspective, training staff to operate blockchain solutions might be a concern. We can categorize all blockchain-related costing, funding, and economics under an umbrella term that we call enterprise blockonomics. Enterprise blockonomics, blockchain economics, can be defined as a study of cost and cost models in the context of enterprise blockchains. With that, we have covered a lot of background material and developed an understanding of the enterprise blockchain requirements, architecture, and challenges. Let's now dive into some examples of enterprise blockchain platforms. First, we'll discuss Corda and then Quorum. Corda. Corda is not a blockchain by definition because it does not use blocks for batching transactions. Still, it is a distributed ledger and provides all benefits that a blockchain can. Traditional blockchain solutions have the concept of transactions that are bundled together in a block, and each block is linked back cryptographically to its parent block, providing an immutable record of transactions. This is not the case with Corda. Corda has been designed entirely from scratch with a new model for providing all blockchain benefits, but without a traditional blockchain with blocks. It was developed initially for the financial industry to solve issues arising from each organization managing its own local ledgers. This means that each organization has its own view of truth. This situation often leads to contradictions and operational risk. Moreover, data is also duplicated at each organization, which results in an increased cost of managing individual infrastructures and complexity. These are the types of problems within the financial industry that Corda initially aimed to resolve by building a decentralized database platform. Initially, Corda only focused on financial applications, but now has expanded in other areas such as government, healthcare, insurance, and supply chains. Corda has two implementations, Corda Enterprise and Corda Open Source. Both Corda Enterprise and Corda Open Source are interoperable and compatible with one another, and have the same features. However, the Enterprise version is more focused on enterprise requirements. It is a commercial version of the Corda platform targeting business requirements such as privacy, security, and performance. Also, it includes Corda Firewall, high availability nodes, and notaries, and support for hardware security modules. It provides an enterprise-grade platform for use in businesses. The Corda platform, on the other hand, allows direct transaction between businesses. This network provides benefits such as privacy and ready sharing of data, which results in the reduction of complexity and costs. The Corda source code is available at github.com/corda/corda. It is written in a language called Kotlin, which is a statically typed language targeting the Java Virtual Machine, JVM. Architecture. The main components of the Corda platform include the Corda network, state objects, contract code and legal prose, transactions, consensus, and flows. We will explore these in more detail now. Corda network. The Corda network is defined as a fully connected graph. It is a permissioned network that provides direct P2P communication on a need-to-know basis. Unlike other traditional blockchains, distributed ledgers, there is no global broadcast or gossip protocol. The communication occurs directly on a point-to-point basis between interested parties. Peers or nodes communicate using the AMPQ serialization protocol. A service called Network Map Service is responsible for publishing a list of peers. A high-level architecture diagram of the Corda network is shown here, showing different components. State objects. State objects represent the smallest unit of data that constitute a financial agreement. These objects are digital documents that describe and fully capture all information about a shared agreement between parties. They are created or deleted as a result of transaction execution. State objects refer to the contract code and legal prose. Legal prose is optional and provides legal binding to the contract. However, contract code is mandatory to manage the state of the object. It is required to provide a state transition mechanism for the node, according to the business logic defined in the contract code. State objects contain a data structure that represents the current state of the object. A state object can be either current, live, or historic, no longer valid. For example, in the following diagram, a state object represents the current state of the object. In this case, it is a simple mock agreement between Party A and Party B, where Party A has paid Party B 1,000 British pounds. This represents the current state of the object. However, the referred contract code can change the state via transactions. State objects can be thought of as a state machine, which is consumed by transactions to create updated state objects. States define the facts regarding which the agreement is achieved. Transactions. Transactions are used to perform transitions between different states. For example, the state object shown in the preceding diagram is created as a result of transaction. Corda uses a Bitcoin-style UTXO-based model for its transaction processing. The concept of state transition by transaction is the same as in Bitcoin. Similar to Bitcoin, transactions can have single, multiple, or no inputs, and single or multiple outputs. All transactions are digitally signed. Moreover, Corda has no concept of mining because it does not use blocks to arrange transactions in a blockchain. Instead, notary services are used to provide a temporal ordering of transactions. In Corda, new transaction types can be developed using JVM bytecode, which makes it very flexible and powerful. Consensus. The consensus model in Corda is quite simple and is based on notary services, which will be discussed in the Corda section of this chapter, under Components. The general idea is that the transactions are evaluated for their uniqueness by the notary service, and if they are unique, that is, unique transaction inputs, they are signed by consensus services as valid. There can be single or multiple clustered notary services running on a Corda network. Various consensus algorithms like PBFT or Raft can be used by notaries to reach consensus, but the core idea is to check whether a proposed transaction is a valid update for the ledger or not. There are two types of consensus in Corda: validity consensus and uniqueness consensus. Validity consensus. This ensures that the contract of every input and output state accepts the proposed transaction. The transaction possesses all required signatures. Note that this process doesn't just verify the proposed transaction itself. It also verifies every previous transaction in the entire chain of the transactions. In other words, it validates all transactions behind this transaction that ultimately resulted in the creation of the inputs of the proposed transactions. This is called walking the chain. Uniqueness consensus. This provides validity consensus over the state's validity and consensus over state uniqueness. The first mechanism is concerned with the validation of the transaction, ensuring that all required signatures are available and the states are appropriate. The second mechanism is a means to detect double spend attacks and ensures that a transaction has not already been spent and is unique. Uniqueness consensus is only checked by a notary service. In contrast, validity consensus is verified by each required signer before signing the transaction. This ensures that one of the input of a proposed transaction has already been spent, consumed in another transaction. Flows. Flows in Corda are a novel idea that allows the development of decentralized workflows. All communication on the Corda network is handled by these flows. These are transaction-building protocols that can be used to define any financial flow of any complexity using code. Flows run as an asynchronous state machine and they interact with other nodes and users. During their execution, they can be suspended or resumed as required. Core the apps. The core model of Corda consists of state objects, data, transactions, and transaction protocols that, when combined with contract code, allowed operations, APIs, wallet plugins, and user interface components, result in constructing a Corda distributed application. A Corda distributed application is a distributed application that runs on a Corda network. It allows nodes on the network to reach an agreement regarding updates to the ledger. For this purpose, flows are defined that describe a routine for the node to execute. Smart contracts in Corda are written using Kotlin and/or Java. The code is targeted at the JVM. The JVM in Corda has been modified to achieve deterministic results of the execution of JVM bytecode. There are three main components in a Corda smart contract as follows. Executable code, which defines the validation logic to validate changes to the state objects. State objects represent the current state of a contract and can either be consumed by a transaction or created by a transaction. Commands are used to describe the operational and verification data that defines how a transaction can be verified. In this section, we saw that a core DApp is a distributed application that can be developed in Kotlin or Java and runs on a Corda network. Core DApps provide a mechanism for nodes to reach an agreement. Next, we'll explore some of the components required in the Corda network. Components. The Corda network has multiple components. These components are described as follows. Nodes. A node is a JVM runtime with a unique identity on the network. It has a network layer that allows interaction with other nodes and an RPC interface that will enable the node's owner to interact with it. A node hosts core DApps and Corda services. Nodes in a Corda network operate under a trustless model and are run by different organizations. Each node has an agreed and verified IP address. IP addresses belong to organizations who run nodes and also go through a KYC process. Nodes run as part of an authenticated P2P network and communicate directly with one another using the Advanced Message Queuing Protocol, AMQP. AMPQ is an approved international standard, ISO IEC 19464, and ensures that messages across different nodes are transferred safely and securely. AMQP works over Transport Layer Security, TLS, in Corda, thus ensuring privacy and integrity of data communicated between nodes. Nodes also make use of a local relational database for storage. Messages on the network are encoded in a compact binary format. They are delivered and managed by using the Apache Artemis message broker, ActiveMQ. A node can serve as a network map service, notary, oracle, or a regular node. The following diagram shows a high-level view of a Corda node. The key elements of a Corda node are a persistence layer, which consists of a vault and storage service. It is responsible for storing data in a local SQL database. A network interface, which enables communication with other nodes as part of running a flow. An RPC interface is responsible for providing interface for interaction with the node's owner via RPC clients and/or web servers. It exposes a number of RPC operations for node and flow management, administration, and retrieving information about flows, nodes, and the network. A service hub enables flows in the node to call other services utilities in a node, such as storage and vault services. A core DApp interface and provider which allows the extending of a node with core DApps. Next, we'll discuss the permissioning element of Corda, which controls network membership, the permissioning service. The permissioning service doorman is used to provision TLS certificates for security. Participants are required to have a signed identity issued by a root certificate authority to participate in the network. Identities are required to be unique on the network. The permissioning service is used to sign these identities, and the naming convention applied to recognize participants is based on the X.500 standard. This ensures the uniqueness of the name. Doorman is responsible for performing KYC and permitting nodes to join and use the network. Network Map Service. This service is used to provide a network map in the form of a document of all nodes on the network. This service publishes IP addresses, identity certificates, and a list of services offered by nodes. All nodes announce their presence by registering to this service when they first start up, and when a connection request is received by a node. The presence of the requesting node is checked on the network map first. Put another way, this service resolves the identities of the participants to physical nodes. Notary Service. In traditional blockchains, mining is used to ascertain the order of blocks. In Corda, notary services are used to provide transaction ordering and time-stamping services. There can be multiple notaries in a network, and they are identified by composite public keys. Notaries can use different consensus algorithms like BFT or Raft, depending on the requirements of the applications. Notary services sign the transactions to indicate the validity and finality of the transaction, which is then persisted to the database. Notaries can be run in a load balance configuration to spread the load across the nodes for performance reasons. The nodes are recommended to be run physically closer to the transaction participants to reduce latency. Due to the distributed nature of distributed ledgers, there is no exact universal time in the network. Therefore, it is always difficult to say when precisely an event occurred. In Corda, time windows can be used to assert that a transaction happened after a specific event or time. A transaction in Corda can include a time window that enforces timing restrictions on the commitment of the transaction. This means that the transaction can only be notarized and committed during the time window specified in the transaction. The notary can serve as a time-stamping authority. Before notarizing a transaction, it can verify that a transaction occurred during a specified time window. Time windows allow us to build scenarios that can indicate whether a transaction happened before an event or after a specific time. This can be useful in constructing scenarios where we can say, for example, a transaction happened after the expiry of a contract, or after some event, or on a specific day. It is important that a notary has an accurate and valid time feed for this function to work correctly. Oracle Service. Oracle services either sign a transaction containing a fact if it is true, or can themselves provide factual data. They allow real-world feed into the distributed ledgers. Oracles were discussed in Chapter 10, Smart Contracts. Transactions. Transactions in a Corda network are never transmitted globally, but in a semi-private network. They are shared only between a subset of participants who are related to the transaction. This is in contrast to traditional blockchain solutions like Ethereum and Bitcoin. where all transactions are broadcast to the entire network globally. Transactions are digitally signed and either consume state or create a new state. Transactions on a Corda network are composed of the following elements. Input references. This is a reference to the states that transaction is going to consume and use as an input. Output states. These are new states created by the transaction. Attachments. This is a list of hashes of attached zip files. Zip files can contain code and other relevant documentation related to the transaction. Files themselves are not made part of the transaction. Instead, they are transferred and stored separately. Commands. A command represents the information about the intended operation of the transaction as a parameter to the contract. Each command has a list of public keys, which represents all parties that are required to sign a transaction. Signatures. This represents the signature required by the transaction. The total number of signatures required is directly proportional to the number of public keys for commands. Type. There are two types of transactions, namely normal and notary changing. Notary changing transactions are used for reassigning a notary for a state. Timestamp. This field represents a bracket of time during which the transaction has taken place. These are verified and enforced by notary services. Also, it is expected that if strict timings are required, which is desirable in many financial services scenarios, notaries should be synchronized with an atomic clock. Summaries. This is a text description that describes the operation of the transaction. Vaults. Vaults run on a node and are similar to the concept of wallets in Bitcoin. As the transactions are not globally broadcasted, each node will have only that part of data in their vaults that are considered relevant to them. Vaults store their data in a standard relational database and, as such, can be queried by using standard SQL. Vaults can contain both on-the-ledger and off-ledger data, meaning that it can also have some part of the data that is not on the ledger. Vaults keep track of spent and unspent states. Other tools. Other important tools in Corda are described as follows. Application Firewall. This is an enterprise feature that operates like a reverse proxy and helps to run Corda behind corporate firewalls. It is an optional component that acts as a reverse proxy for Corda nodes residing behind the demilitarized zone, DMZ, which is usually the case in an enterprise. The application firewall helps to minimize the amount of code that runs on a network's DMZ, thus reducing the attack surface. It enables secure AMQP TLS 1.2 interaction with Corda peer nodes outside the corporate network. It works as an application-level firewall for internet-facing endpoints on the Corda network. The firewall has two components called the bridge and the float. The bridge handles outbound connections, whereas the float handles the inbound connection. A single instance of the Corda firewall can serve multiple nodes. Network Simulator. This is a visualization tool that shows traffic between nodes and the network setup via a map service. Node Explorer. This is another visualization tool that allows us to view transaction information. Load Tester. This, as the name suggests, helps to stress test nodes under various extreme scenarios. Transaction Flow. In this section, we'll explore how, when a request is sent to a node, Corda accepts the request and responds. The flow process can be summarized as follows. 1. An HTTP request via API or RPC call is made directly to flows in Corda. This is a request to start a transaction. 2. Start a flow. Flows contain the business logic. 3. Perform initial steps such as transaction building and verification. 4. Obtain counterparty signatures. 5. Sign the transaction and check signatures. 6. Obtain notarization finality. 7. Record the transaction and store it in persistent storage and vaults. 8. respond via an HTTP response through API. This process can be visualized using the following diagram. A Corda app is a functional aspect of the Corda network and contains the business logic for a use case. The Vault database is used to store states via JDBC. Corda nodes communicate using AMQP TLS 1.2. Node administrators use SSH to interact with the node. An identity certificate is issued to a node via the doorman service, which works over HTTPS. Corda nodes discover other nodes on the network via the network map service over HTTPS. Corda nodes and the Corda firewall service make sure that a certificate is currently valid by checking CRLs, which is performed over an HTTP or HTTPS connection. Now, let's see how we can set up a development environment to explore Corda's codebase. We have not provided any specific development application, but have provided links where official examples are available. Corda Development Environment. The development environment for Corda can be set up easily using the following steps. The required software consists of the following: JDK 8, 8U131, IntelliJ IDEA Community Edition, H2 Database Platform Independent Zip, Git, Kotlin language. Gradle is another component that is used to build Corda. Once all these tools are installed, smart contract development can be started. Corda apps can be developed by utilizing an example template. Corda can be cloned locally from GitHub using the following command: $git clone https://github.com/corda/corda.git. Once entered in the operating system terminal, this command will clone the repository into a local directory named Corda. Once the repository is cloned, it can be opened in an IntelliJ development environment for further development. There are multiple samples available in the repository, such as a bank of Corda, interest rate swaps demo, and traders' demo. You may find it useful to explore these demos to understand how Corda apps are developed. These samples are available under the samples directory under Corda, and they can be explored using IntelliJ IDEA IDE. With this, we've completed our introduction to the Corda platform. Now we'll cover Quorum, another popular blockchain platform, in detail. Quorum. Quorum is an open-source enterprise blockchain platform. It is a lightweight fork of Ethereum. Quorum not only benefits from the innovation and research being done in the upstream public Ethereum Geth project, but also many excellent enterprise features have been introduced in Quorum. These enterprise features primarily focus on providing enterprise-grade privacy, performance, and permissioning access control. In this section, we'll explore Quorum's architecture in detail and see a practical example of how to set up a Quorum network. First, let's take a look at Quorum's architecture. Quorum addresses three fundamental issues in public blockchains, which makes Quorum an excellent choice for enterprise use cases: privacy, performance, enterprise governance. At a high level, the Quorum architecture consists of nodes and their associated privacy managers. The Quorum node is a modified and enhanced version of public Geth that supports private transactions. Quorum nodes communicate via HTTPS with privacy managers who, in turn, are responsible for providing privacy by storing the payload in encrypted format in their local storage. These Quorum nodes maintain the public and private states separately. Architecture. The Quorum architecture can be visualized using the following diagram. There are a number of changes that have been made to Quorum Client to make it suitable for enterprise use cases. We'll provide an overview of each of those changes here. Enhance P2P. This layer is modified to allow connections only between authorized nodes. Enhance State, Private and Public. In addition to the public state tree, there is an additional Merkle-Patricia state tree for the private state. Pluggable consensus. Quorum supports multiple consensus algorithms such as IBFT, Proof of Authority, POA, and Raft. Quorum, being an enterprise blockchain, does not need a POW type of consensus. No transaction fees. The pricing of gas has been set to 0 as there is no need for transaction fees in consortium networks. Private transactions. Private transactions are identified using 37 or 38 as the v-value in the transaction. The transaction creation mechanism is modified to enable replacing transaction data input with the hash of the encrypted payload. Modified block generation mechanism. The lock for generating blocks is modified with a new check for the global public state root instead of the global state root. Modified block validation mechanism. Block validation logic is modified to replace the global state root check with the global state root check for public state, otherwise known as a global public state root. Enhance RPC API. Quorum supports additional RPC APIs that help us interact with the enhanced enterprise features of Quorum, such as permissioning and consensus mechanisms. Now we'll discuss Privacy Manager, which consists of two components, a transaction manager and an enclave. Privacy Manager. Privacy Manager is an off-chain mechanism that provides transaction confidentiality. It is paired on a one-to-one basis with a Quorum node. It allows Quorum nodes to share the transaction payload securely between authorized participants. It is composed of two components, the Transaction Manager and the Enclave. Transaction Manager. The Transaction Manager is responsible for storing encrypted transaction payloads, managing access to encrypted transaction payloads, propagating encrypted payloads to other transaction managers on the network, discovering other transaction managers on the network. Quorum has developed two transaction managers. Initially, a Haskell implementation called Constellation was made available. However, it is no longer actively developed in favor of a more feature-rich Java-based privacy manager called Tessera. Tessera is developed in Java. It is used for storage, encryption, decryption, and propagation of private transaction data. Enclave. An enclave is an isolated and independent element that provides cryptography services for transaction payload encryption and decryption. It can only be associated on a one-to-one basis with its own transaction manager. In order to achieve all the desired privacy features, several cryptographic protocols and primitives have been used in the Quorum platform. We'll provide a quick overview of these in the next section. Cryptography used in Quorum. Quorum inherits its cryptography stack from public Ethereum. It includes standard ECD-SA signatures, AES CTR cryptography for wallets, and Dev P2P and CACAC 256 hash functions. Privacy Manager makes use of Curve 25519, Elliptic Curve Diffie-Hellman ECDH, Poly 1305, and Z-Salsa 20 cryptographic operations to provide confidentiality guarantees required by private transactions in Quorum. Now we'll explore how each of the main facets, privacy, confidentiality, enterprise-grade membership control, access control, and the permissioning mechanism and performance are achieved in Quorum. Privacy. Quorum supports both private and public transactions. For private transactions, it uses a mechanism called Private Transaction Manager, which is an off-chain component to facilitate the confidentiality of transactions. We will now describe how private transactions work in Quorum. Suppose there are three parties, A, B, and C. Parties A and B are privy to a transaction, while party C is not. We'll now explore how the private transaction is generated and flows between parties and propagated on the network, while maintain confidentiality. Let's call this transaction Transaction AB. 1. To begin private transaction AB, party A creates a transaction and signs it before sending it to their Quorum node, node A. The transaction is composed of a transaction payload and the public key of the intended recipient. This list of public keys of intended recipients is maintained in the private for list. It can be a single public key or multiple depending on the requirements. 2. Quorum node A sends the transaction to Transaction Manager A for processing. 3. Transaction Manager A makes an encryption request to its enclave to encrypt the transaction payload. 4. Party A's enclave encrypts the transaction payload and sends it to Transaction Manager A. 5. Transaction Manager A stores the transaction payload and sends it to other transaction managers, in this case B. 6. A transaction hash is returned to Quorum node A by Transaction Manager A, which replaces the original transaction payload with the hash and changes the value V of the transaction to 37 or 38 to indicate that the transaction is private. 7. The transaction propagates to other nodes via the normal Ethereum P2P protocol. 8. The block that contains transaction AB finalizes and propagates on the network between all nodes A, B, and C. 9. When the block containing the transaction is received by the quorum nodes, they recognize the transaction as private because the V value of the transaction is either 37 or 38. If the transaction is identified as private, the quorum nodes will inquire their respective transaction managers to figure out if they are party to the transaction or not. This is achieved by finding out that if there is an entry available in the database with the transaction hash, here parties A and B will have the transaction hash stored in the transaction manager, whereas party C will not. 10. The transaction managers of parties A and B make a transaction payload decryption request to their respective enclaves. 11. The enclaves of party A and B decrypt the private transactions. 12. When the transaction managers receive the decrypted payload back from their enclaves, they send this data to their respective quorum nodes. In our example, the transaction managers of parties A and B will send the transaction payload to their respective quorum nodes A and B. The quorum nodes will execute the transaction contract via the EVM and update their private state database accordingly. The transaction manager of party C will return a message back to its quorum node, indicating that it is not privy to or a recipient of the transaction. This means that the quorum node of party C will simply ignore the transaction. This process can be visualized using the following diagram. Let's now expand on step 4 from the achieving privacy process, enclave encryption, as it consists of a number of sub-steps that are performed within the enclave. Enclave encryption. When an enclave receives a transaction, it performs several steps to encrypt the transaction. All these steps are shown here and are performed by the enclave as part of the transaction payload encryption process. 1. Generates a symmetric key for a transaction. 2. Generates 2 random nonces. 3. Encrypts the transaction payload and one of the nonces with the symmetric key generated in the first step. 4. Encrypts the transaction key for transactions for each recipient. For this purpose, the following steps are performed. A. Generates a shared symmetric key by utilizing ECDH. ECDH will use the sender's private key and the receiver's public key. B. Encrypts the symmetric key for a transaction for each receiver separately using the newly generated shared symmetric key and the second nonce. C. This step will be repeated for each recipient. 5. Finally, the transaction manager receives the encrypted transaction payload, all the encrypted symmetric keys for transactions, both nonces, and the public keys of the senders and receivers. Now let's see how the transaction manager stores and propagates transactions to the other transaction manager. We'll now expand on step 5 of the achieving privacy process mentioned previously. Transaction propagation to transaction managers. A transaction manager performs the following steps after it receives an encrypted response back from the enclave. 1. It generates the SHA-3 512 hash of the encrypted payload received from the enclave. 2. It stores the encrypted payload, the hash, and encrypted symmetric key for the transaction. both nonces and the public keys of the sender and receiver. 3. It sends using HTTPS the encrypted payload, the hash, and the encrypted symmetric key. 4. The transaction using Transaction Manager B's public key to Transaction Manager B. 4. Transaction Manager A awaits an acknowledge message from Transaction Manager B. If acknowledgement is not received, the transaction will not be propagated to the network. Let's now discover how the decryption process works in enclaves. This corresponds to step 11 of the Achieving Privacy process. Enclave decryption. The transaction payload decryption process starts when a transaction payload decryption request is made to an enclave. The enclave performs the following steps to decrypt a payload. 1. Derives the shared symmetric key. The key derivation process works as follows. Party A, being the sender of the transaction, derives the shared symmetric key using its private key and receiver's public key. B. Party B, being the recipient of the transaction, derives the shared symmetric key using its private key and the sender's public key. 2. Decrypts the symmetric key for transactions with the shared symmetric key along with the encrypted payload and nonce fetched from the database. 3. Decrypts the transaction data with the symmetric key for transactions and the encrypted data and nonce fetched from the database. 4. Finally, the decrypted private transaction data is sent to the transaction manager. The overall process, enclave encryption, transaction manager storage and propagation to other nodes, and enclave decryption, corresponding to steps 4, 5, and 11 in Figure 21.10, can be visualized in the following diagram. We've covered quite a lot of theory here, but with this we have now completed our introduction to quorum private transactions. Next, we'll explore how access control works in quorum. Access control with permissioning. As an enterprise blockchain platform, Quorum comes with an enterprise-grade access control mechanism that manages network membership for consortium members. It is implemented in smart contracts written in the Solidity language. It supports many features that a typical enterprise-grade permissioning mechanism would. It includes features to support the management of nodes, account-level permissioning, and support for voting-driven decision-making for permissioning actions. The overall architecture of Quorum's permissioning mechanism can be visualized using the following diagram. This permissioning mechanism is inspired by a widely accepted industry standard called Role-Based Access Control, RBAC. It is standardized by the American National Standards Institute, ANSI, and is used in most enterprise-grade software, such as operating systems and cloud systems. The features that Quorum's permission mechanism supports are listed here. Role management, assignment of roles to accounts, subjects. Permissions management, node management. At a fundamental level, the permissions management model supports granular control over funds transfer, smart contract creation, smart contract execution. It controls which account can transfer funds, create smart contracts, or execute smart contracts. These permissions are used to create roles, which are then assigned to accounts to enforce permissions. Permissions are divided into two broad categories: account permissions, which control what functions an account can perform, and node permissions, which control membership of nodes on the network. Accounts can be assigned with different roles and statuses, whereas nodes can be assigned with statuses. Statuses for accounts include several statuses such as active, inactive, suspended, and blacklisted. Nodes can be in approved, deactivated, pending approval, or blacklisted states. The access types can be read-only, transact, contract deploy, and full access. Now that we have covered how enterprise-grade permissioning is implemented in Quorum, let's now move on to another important aspect of enterprise blockchain: performance. Performance is a vast subject and can mean different things in different scenarios. Mostly, it is merely a measure of how many transactions a system can perform in a given interval, usually measured in transactions per second, TPS. It can also mean overall throughput of the system, quality of the service, and the ability to scale. From a business perspective, it could mean business performance. However, here we will only deal with the TPS scenario and present some studies that have been performed to evaluate the performance of the Quorum blockchain. The core idea behind performance enhancement in the Quorum blockchain is the usage of deterministic and fast consensus algorithms. Quorum supports various consensus mechanisms suitable for consortium networks. As compared to other public blockchain consensus mechanisms, the algorithms used in Quorum provide better performance. Several evaluations have been made and reported regarding Quorum's performance. These studies have reported Quorum's performance to be as high as 2,500 TPS. Now we'll introduce the consensus mechanism supported by Quorum. Pluggable consensus. Quorum supports several consensus algorithms that can be plugged in based on use case requirements. For example, if the requirement is simple crash tolerance, users can choose Raft. If more security is required, and Byzantine faults need to be handled, then users can choose IBFT. We have listed the consensus mechanisms available in Quorum here. Raft, a crash fault-tolerant consensus algorithm. IBFT, a PBFT-inspired BFT algorithm. Click, Proof of Authority POA inherited from public Ethereum. We discussed all these algorithms in detail in Chapter 5, Consensus Algorithms. You can review these topics in detail there. Now that we have gone through several features and have built a theoretical understanding of various features of the Quorum Enterprise blockchain, let's now see how we can set up a Quorum network. Setting up Quorum with IBFT. In this section, we will set up a Quorum network with 4 nodes, demonstrating how an IBFT network can be set up and carry out private transactions in Quorum. These steps can be performed manually, or we can use a tool called Quorum Wizard to quickly and easily spin up a Quorum network. We will use Quorum Wizard to set up your network. Quorum Wizard. Quorum Wizard is a command line tool written in JavaScript that enables users to create a local network of Quorum nodes quickly. It runs as an NPM module and, as such, requires Node.js and NPM to run. Node.js can be installed from this address, nodejs.org. To check the current version installed, issue the following command, $npm-v. This command will produce the following output, indicating the installed version of Node Package Manager NPM, 6.14.4. This command will show the currently installed version of Node, $node-v. This will produce an output specifying the version of Node you have installed, v12.18.0. If the expected version number is displayed after executing both of these commands, then we are all set up to install Quorum Wizard, which we'll describe in the next section. Installing Quorum Wizard. Quorum Wizard can be installed using npm install. It's an excellent tool and cuts installation time down from hours to minutes. $npm install-g quorum-wizard. This will show an output similar to the one shown here. Once installed, we can run it with the following procedure. Running Quorum Wizard to create a new network. We will create a 4-node IBFT network in this example. Simply run Quorum Wizard and follow the steps as prompted. $quorum-wizard. Running Quorum Wizard will show the following text. Select Simple Network and select all the options by using the up and down arrow keys as shown here. Press Enter after a choice is made, which will move us on to the next question in Wizard. Once all the options have been selected as shown in the preceding code snippet, the tool will download and install dependencies. This process will produce an output similar to the one shown here. For brevity, the full output is not shown. Finally, the output shown here is produced, indicating the success of the operation. Now change to the 4 nodes Istanbul Tessera bash directory, as shown here, and start the network. This will produce an output similar to the one shown here. Some of the output has been truncated for brevity. And that's it. We now have a quorum network with 4 nodes running on the IBFT protocol. We can also visualize the network using Cakeshop, which we'll describe next. Cakeshop. Cakeshop is a powerful visualization and administration tool with different features such as node management, block explorer, and contracts management. Cakeshop is installed as part of the Quorum Wizard network creation process. Once the network runs successfully, we can browse to localhost :8999 where Cakeshop runs. Cakeshop is shown in the following screenshot. Now let's do an experiment to see how private transactions can be created and run on the Quorum network. Quorum Wizard has already created the relevant scripts. Running a private transaction. In this section, we will explore how private transactions can be created and executed on a Quorum network. 1. From within the 4 nodes Istanbul Tessera bash directory, run the command shown here. $4-nodes-Istanbul-Tessera-bash.runscript.sh private_contract.js. Once the preceding command runs, it will produce an output similar to the one shown here, indicating that the transaction has been sent and that a transaction hash has been produced. Here we have basically executed a private transaction and deployed a private smart contract that is only visible to Node 1 and Node 2. Nodes 3 and 4 are not party to this transaction, and they shouldn't be able to view the contents of the code or the value state of the contract. We will demonstrate in this example that this is indeed the case. Next, we'll attach geth to each node as shown using the commands in the following sections and run the console commands as shown in the examples for each node. Node 1. In order to interact with geth via IPC, enter the following command in the operating system's terminal. This will open the geth JavaScript console, where users can interact with the blockchain using several methods exposed by geth. $geth attach qdata/dd1/geth.ipc. Once the geth console is open, enter the following command which declares a variable named ABI. Now create a new contract instance using the command shown here. We can use this object to access all methods and events of the contract. > var simple contract equals eth.contract open parentheses ABI close parentheses. Next, we use the instance object created previously to get a complete abstraction of our contract by using the command shown here. > var simple equals simple contract.at. Now we can use the simple object to access all the methods in our smart contract. In the following example, we're using the get parentheses method to return the stored value in our contract. This command outputs 42, which is our stored value. Note that after each statement we enter in the geth console, except the last statement, simple, get, parentheses, we also see that a message of undefined is displayed. Simply ignore this. It is just a standard way in JavaScript of indicating uninitialized variables, non-existent object properties, or other similar scenarios. Node 2, similar to Node 1, open the geth console for Node 2 using the command shown here. $geth attach qdata/dd2/geth.ipc. As we did for Node 1 in the geth console, enter the following commands. Much like Node 1, the final command outputs 42, which is our stored value. Node 3, again similar to Node 1, open the geth console for Node 3 using the command shown here. $geth attach qdata/dd3/geth.ipc. In the geth console, enter the following. Note that the value returned is 0, which indicates that Node 3 cannot access the value of 42, which is expected as Node 3 is not privy to the transaction. Node 4. Finally, we open the geth console for Node 4 using the command shown here. $geth attach qdata/dd4/geth.ipc. In the console, enter the following command as we did for nodes 1, 2, and 3. As expected, nodes 3 and 4, which are not party to the transaction, will see 0 as the transaction value. On the other hand, nodes 1 and 2 are able to see the transaction value, which is 42. In the next section, we'll see how we can use Cakeshop to view the transactions and other relevant blockchain data. Remember, as we discussed earlier in this chapter, we need to monitor and visualize enterprise blockchain networks. Cakeshop fulfills that need. Viewing the transaction in Cakeshop. In Cakeshop, we can see this transaction and relevant attributes. We simply browse to Chain Explorer and enter the transaction hash from step 1 of this process. Cakeshop will display the status of the transaction, block ID, block number, contract address, and several other attributes, which makes it easy to explore the transaction process in detail. Further investigation. We can also see the transaction receipts and contract code using the Geth console. For this, we attach to Geth using the following command: $Geth attach. We will do this on each node as follows. Node 1, first we open the Geth console using the following command on node 1. $Geth attach qdata/d1/geth.ipc. When the Geth console opens, enter the following statement which uses the transaction hash from our first step of contract deployment. The output shown here will be displayed. In the preceding output, we can see that the V value is 0x26 in hexadecimal, which means 38 in decimal. This value of 38 indicates that the transaction is private. Also notice the input field, which is the encrypted payload of the transaction. Similarly, we can get the transaction receipt of this transaction by issuing the call shown here. We can see in the output that the status is 0x1, indicating the success of the transaction, as we need to get the code of this transaction, smart contract. We need the contract address, which we can see in the contract address field. We copy that address into the RPC call shown here to fetch the code for this contract. As we can see in the preceding output, the contract code is visible as bytecode and hex. Node 2, which is privy to the transaction. Similarly to Node 1, open the Geth console on Node 2 using the command shown here. $Geth attach qdata/dd2/geth.ipc. In the Geth console, enter the following statement. This method takes the address of the smart contract and returns the compile smart contract code, bytecode. The following output shows the bytecode of our contract address. As expected, the code is also visible on Node 2 as Node 2 is party to the transaction. Node 3, which is not privy to the transaction. Now we open the Geth console on Node 3. In the console, enter the following statement with the address of our smart contract, _f.getCode, parentheses. This will show the output shown here. This output indicates that the contract code is only available on the nodes that are party to the transaction. The contract code is not available on other nodes that are not a party to the transaction. This experiment demonstrates that the contract is only available on the nodes that are party to the transactions. First, we deployed our private contract from Node 2 with Node 1 as a participant and used the Geth console to interact with the contract. We saw that the value 42 is only available on the nodes that are party to the transaction. Also, we further experimented and noticed that not only the value but the smart contract code is only available on the nodes that are party to our private contract transaction. This network is now available for further experiments. You can create your own private contracts with different nodes as parties. You can also explore how other methods such as debug_trace transaction behave when interacting with private contracts. This network can also be used to build some POCs for an enterprise app. After this quick experiment of demonstrating how private transactions work in Quorum, let's explore other Quorum projects. As mentioned earlier, Quorum is a feature-rich platform and is under continuous improvement and development. As a result, new features and projects are introduced regularly. Some of the other projects under Quorum are listed here, along with brief descriptions. Other Quorum projects. Some of the projects and features are listed here. Remix plugin. This is a plugin for the popular Remix IDE, which supports private smart contracts on the Quorum blockchain. Pluggable architecture. Quorum supports a pluggable architecture that allows us to add new features to the Quorum client as plugins. This approach allows us to keep the core Quorum services separate from the new features, which allows greater modularity and extensibility without modifying the core client. Quorum is a large project with many excellent enterprise features. It is not possible to cover all of them in this chapter. However, the material provided should get you started with Quorum blockchain setup, plus an understanding of the concept of private transactions. Quorum has been used in many industries for different projects, including finance, supply chain, healthcare, media, and government sectors. A couple of example uses are here: tracking luxury goods, post-trade processing platform. Quorum is also available on different cloud platforms, including Azure and Kaleido. Summary: in this chapter, we started with an introduction to enterprise solutions and blockchain. We saw some limiting factors in public chains that make them suitable for enterprise use cases. We also looked at some requirements that, when met, will make a blockchain suitable for enterprise use cases. We also covered how to design enterprise blockchain solutions and made a case to see the enterprise blockchain solutions in the context of the enterprise architecture. Next, we explored cloud computing and the definition of blockchains as a service. We briefly looked at the efforts being made to standardize enterprise Ethereum specifications. The last sections of this chapter covered enterprise blockchain platforms, including Quorum and Corda. And finally, we set up an IBFT network using Quorum to demonstrate how privacy is achieved using Quorum. In the next chapter, we will introduce scalability, security, and other challenges that blockchains face. How many of these limitations are being addressed, and what the future holds for the blockchain technology.
Chapter 21: Scalability and Other Challenges. This chapter aims to explore various challenges that need to be addressed before blockchain can become a mainstream technology. Despite the fact that multiple use cases and proof-of-concept systems have been developed, and that the technology works well for many scenarios, there still is a need to address some fundamental limitations that are present in blockchains to make the technology more adoptable. At the top of the list of these issues comes scalability and then privacy, both of which are significant limitations. The lack of scalability is a general concern, where blockchains do not meet the adequate performance levels expected by users when the chain is used on a large scale. Privacy is also of utmost importance, especially as blockchains are envisioned to be used in privacy-demanding industries. There are specific requirements around the confidentiality of transactions in the finance, law, and health industries, for example. These two issues are becoming inhibiting factors toward blockchain technology's broader acceptance. A review of currently proposed and ongoing research in these two specific areas will be presented throughout this chapter. In addition to scalability and privacy, other challenges facing blockchain include regulation, integration, interoperability, adaptability, and security in general. Although in blockchains, generally, security is quite good. For example, Bitcoin has stood the test of time and is still extremely secure. There still are some caveats that may allow security to be compromised. Moreover, there are some reasonable security concerns in other blockchains such as Ethereum regarding smart contracts, denial of service (DOS) attacks, and a large attack surface. All of these will be discussed in detail in the following sections, which are as follows:
scalability, privacy, security, other challenges. Now we'll start with scalability, one of blockchain's biggest challenges. Scalability. This problem has been a focus of intense debate, rigorous research, and media attention for the last few years. This is the single most important problem in blockchain, which could mean the difference between the wider adaptability of blockchains or limited private use only by consortiums. As a result of substantial research in this area, many solutions have been proposed, which are discussed in the following section. From a theoretical perspective, the general approach toward tackling the scalability issue generally revolves around protocol-level enhancements. For example, a commonly mentioned solution to Bitcoin scalability is to increase its block size. This would mean that a larger number of transactions can be batched in a block, resulting in increasing scalability. Other proposals include solutions that offload certain processing to off-chain networks, for example, off-chain state networks. Based on the aforementioned solutions, generally the proposals can be divided into two categories. On-chain solutions, which are based on the idea of changing fundamental protocols on which the blockchain operates, and off-chain solutions, which make use of network and processing resources off-chain in order to enhance the blockchain. Now we'll introduce an approach that has been proposed to view blockchains as being composed of different planes. We'll then address each plane separately to develop an overall scalability solution. Blockchain planes. Another approach to addressing limitations in blockchains has been proposed by Andrew Miller et al. And others in their position paper on scaling decentralized blockchains. In this paper, it is shown that a blockchain can be divided into various abstract layers called planes. Each plane is responsible for performing specific functions. These include the network plane, consensus plane, storage plane, view plane, and side plane. This abstraction allows limitations at each plane to be addressed individually and in a structured manner, which then results in an overall scalability solution. A brief overview of each layer is given in the following subsections, with some references to the Bitcoin system. Network plane. First, we'll discuss the network plane. The paper on scaling decentralized blockchains mentioned previously identifies that in Bitcoin, the network plane underutilizes network bandwidth in regards to transaction propagation, which is one of its key functions. This limitation transpires due to the way the Bitcoin protocol effectively duplicates transaction broadcasts. First, local transaction validation occurs, where the protocol propagates all transactions. Then, after mining, block propagation occurs, which contains previously disseminated transactions again. Consensus plane. The second layer is called the consensus plane. This layer is responsible for mining and achieving consensus. Bottlenecks in this layer revolve around limitations in proof of work algorithms, whereby increasing consensus speed and bandwidth results in compromising the security of the network due to an increase in the number of forks. Storage plane. The storage plane is the third layer, which stores the ledger. Issues in this layer revolve around the need for each node to keep a copy of the entire ledger, which leads to certain inefficiencies, such as increased bandwidth and storage requirements. Bitcoin has a method available called pruning, which allows a node to operate without the need to keep the full blockchain in its storage. Pruning means that when a Bitcoin node has downloaded the blockchain and validated it, it deletes the old data that it has already validated. This saves storage space. This functionality has resulted in major improvements from a storage perspective. View plane. Next on the list is the view plane, which proposes an optimization based on the proposal that Bitcoin miners do not need the full blockchain to operate, and that a view can be constructed out of the complete ledger as a representation of the entire state of the system, which is sufficient for miners to function. Implementation of views will eliminate the need for mining nodes to store the full blockchain. Sideplane. Finally, there's the sideplane, which represents the idea of off-chain transactions. This is the process whereby the concept of payment or transaction channels is used to offload the processing of transactions between participants. However, it is still backed by the main Bitcoin blockchain. Clearly, this plane-based model can be used to describe limitations and improvements in current blockchain designs in a targeted, structured manner. Also, there are several other general strategies that have been proposed over the last few years that can address the limitations in current blockchain designs, such as Ethereum and Bitcoin. These approaches will be characterized and discussed individually in the following section. Methods for improving scalability. As this is a very active area of research, over the years, many techniques and proposals have been made to address the blockchain scalability problem. In this section, we'll introduce many of these techniques. We can divide approaches to solving scalability issues into three main categories, based on the layer in the blockchain stack they operate on. We describe these categories here. Layer 0 methods or network layer methods, where the mechanisms to improve scalability operate at the network level of the blockchain architecture stack. Layer 1 methods are also called on-chain methods, where the blockchain protocol itself is enhanced to improve scalability. This layer represents the blockchain itself. Layer 2 methods or off-chain methods, where mechanisms that are not part of the blockchain and exist outside of the main blockchain are used to improve the scalability of the blockchain. Scalability has two facets. One is increasing the processing speed of transactions, and the other is the increase in the number of nodes on the network. Both are desirable in many situations. However, speed of transactions is more sought after on public networks. Layer 0 network solutions. We'll describe some of the Layer 0 or network layer solutions in the following sections. CADCast. This is a new protocol that enables fast, efficient, and secure block propagation for the Bitcoin blockchain network. Blocks Root. Another network layer solution is Blocks Root, which aims to address scalability problems by creating a trustless blockchain distribution network. Next, let's move on to some core on-chain solutions or Layer 1 solutions. Layer 1 on-chain solutions. In this section, we'll describe Layer 1 or on-chain solutions which target core blockchain elements such as blocks, transactions, and other on-chain data structures to address the scalability problem. Transaction parallelization. Usually in blockchain designs, transactions are executed sequentially. For example, in Ethereum, all transaction execution is sequential, which allows it to be safe and consistent. This also raises a question that if somehow transaction executions can be done in parallel without compromising the consistency and security of the blockchain, it would result in much better performance. Some suggestions have already been made for Ethereum, for example, easy parallelizability, which introduces a new type of transaction parallelizability in Ethereum, which proposes a mechanism to enable parallel transaction execution in Ethereum. However, at the time of writing, none of these ideas are production ready. Currently, Hyperledger Sawtooth is to be the only blockchain that supports parallel transactions and is ready to be used in production. We discuss Sawtooth in detail in Chapter 17, Hyperledger. Increase in block size. This is the most debated proposal for increasing blockchain performance, transaction processing throughput. Currently, Bitcoin can process only about 3 to 7 transactions per second, which is a major inhibiting factor in adapting the Bitcoin blockchain for processing microtransactions. Block size in Bitcoin is hard-coded to be 1 megabyte, but if the block size is increased, it can hold more transactions and can result in faster confirmation time. There are several Bitcoin improvement proposals made in favor of block size increase. These include BIP 100, BIP 101, BIP 102, BIP 103, and BIP 109. In Ethereum, the block size is not limited by hardcoding. Instead, it is controlled by a gas limit. In theory, there is no limit on the size of a block in Ethereum because it's dependent on the amount of gas, which can increase over time. This is possible because miners are allowed to increase the gas limit for subsequent blocks if the limit has been reached in the previous block. Bitcoin Segregated Witness (SegWit) has addressed this issue by separating witness data from transaction data, which resulted in more space for transactions. Other proposals for Bitcoin include Bitcoin Unlimited, Bitcoin XT, and Bitcoin Cash. You can refer to Chapter 6 Introducing Bitcoin for more details. Block Interval Reduction. This is another proposal about reducing the time between each block generation. The time between blocks can be decreased to achieve faster finalization of blocks, but it may result in less security due to the increased number of forks. Ethereum has achieved a block time of approximately 14 seconds. This is a significant improvement from the Bitcoin blockchain, which takes 10 minutes to generate a new block. In Ethereum, the issue of high orphaned blocks resulting from smaller times between blocks is mitigated by using the greedy heaviest observed subtree, GHOST protocol, whereby orphaned or stale blocks, also called uncles in the Ethereum chain, are also included in determining the valid chain. Once Ethereum moves to proof of stake, this will become irrelevant as no mining will be required, and almost immediate finality of transactions can be achieved. Invertible Bloom Lookup Tables. This is another approach that has been proposed to reduce the amount of data required to be transferred between the Bitcoin nodes. Invertible Bloom Lookup Tables, IBLTs, were originally proposed by Gavin Anderson, and the key attraction in this approach is that it does not result in a hard fork of Bitcoin if implemented. The key idea is based on the fact that there is no need to transfer all transactions between nodes. Instead, only those that are not already available in the transaction pool of the syncing node are transferred. This allows quicker transaction pool synchronization between nodes, thus increasing the overall scalability and speed of the Bitcoin network. Sharding. Sharding is not a new technique and has been used in distributed databases for scalability, such as MongoDB and MySQL. The key idea behind sharding is to split up the tasks into multiple chunks that are then processed by multiple nodes. This results in improved throughput and reduced storage requirements. In blockchains, a similar scheme is employed, whereby the state of the network is partitioned into multiple shards. The state usually includes balances, code, nonce, and storage. Shards are loosely coupled partitions of a blockchain that run on the same network. There are a few challenges related to inter-shard communication and consensus on the history of each shard. This is an open area of research and has been extensively studied in the context of Ethereum 2.0. Private blockchains. Most private blockchains are inherently faster because no real decentralization is required and participants on the network do not need to mine using POW. Instead, they can only validate transactions. This can be considered as a workaround to the scalability issue in public blockchains. However, this is not the solutions to the scalability problem. Also, it should be noted that private blockchains are only suitable in specific areas and setups such as enterprise environments, where all participants are known. Proof of stake. POS algorithm-based blockchains are fundamentally faster because POS algorithms do not require the completion of time and energy-consuming POW. POS was explained in detail in Chapter 5, Consensus Algorithms. Block propagation. In addition to the preceding proposal, pipelining of block propagation has also been suggested, which is based on the idea of anticipating the availability of a block. In this scheme, the availability of a block is already announced, without waiting for actual block availability, thus reducing the round-trip time between nodes. Finally, the problem of long distances between the transaction originator and nodes also contributes toward the slowdown of block propagation. It has been shown in the research conducted by Christian Decker et al. That connectivity increase can reduce propagation delay of blocks and transactions. This is possible because if at any one time the Bitcoin node is connected to many other nodes, it can speed up the information propagation on the network. An elegant solution to scalability issues will most likely be a combination of some or all of the aforementioned general approaches. A number of initiatives taken in order to address scalability and security issues in blockchains are now almost ready for implementation or already implemented. For example, Bitcoin SegWit is a proposal that can help massively with scalability and only needs a soft fork in order for it to be implemented. The key idea behind so-called SegWit is to separate signature data from the transactions, which resolves the transaction malleability issue and allows block size increase, thus resulting in increased throughput. Bitcoin NG. Another proposal, Bitcoin NG, which is based on the idea of microblocks and leader election, has gained some attention recently. The core idea is to split blocks into two types, namely leader blocks, also called key blocks, and microblocks. Leader blocks. These are responsible for POW, whereas microblocks contain actual transactions. Microblocks. These do not require any POW and are generated by the elected leader every block generation cycle. This block generation cycle is initiated by a leader block. The only requirement is to sign the microblocks with the elected leader's private key. The microblocks can be generated at a very high speed by the elected leader, miner, thus resulting in increased performance and transaction speed. On the other hand, the Ethereum 2.0 MOV paper written by Vitalik Buterin and presented at Ethereum DevCon 2 in Shanghai describes a different vision of a scalable blockchain. This proposal is based on a combination of sharding and an implementation of the POS consensus algorithm. The paper defines certain goals such as gaining efficiency via POS, minimizing block time, and ensuring economic finality, scalability, cross-shard communication, and censorship resistance. DAGs. DAG stands for Directed Acyclic Graph. It is seen as an alternative to blockchain technology. Blockchain is fundamentally a linked list, whereas DAG is an acyclic graph where links between nodes have only one direction. The DAG structure eliminates the need for mining and blocks, which allows parallel creation and confirmation of transactions, thus achieving high transaction throughput. One example of DAG is IOTA cryptocurrency. More information about this can be found at iota.org. Consensus mechanisms. Traditionally, blockchains are based on POW or POS algorithms, which are inherently slow in terms of performance. Especially POW is able to process only a few transactions per second. If a different consensus mechanism such as Raft or PBFT is used, then the processing speed can increase significantly. We examined these concepts in Chapter 5, Consensus Algorithms, in greater detail. So far, we have discussed Layer 0, network-based solutions, and Layer 1, on-chain solutions, to the scalability issue. In the next section, we'll introduce another approach that aims to solve the scalability problem by using off-chain or Layer 2 components. Layer 2, off-chain and multi-chain solutions. Layer 2 solutions are based on the idea that instead of modifying the main chain to achieve scalability, the objective should be to offload some of the processing to faster mechanisms outside of the main underlying chain. Do processing there and then write the result back on the main chain as an integrity guarantee. Several such techniques are described here. State channels. This is another approach proposed for speeding up the transaction on a blockchain network. The basic idea is to use side channels for state updating and processing transactions off the main chain. Once the state is finalized, it is written back to the main chain, thus offloading the time-consuming operations from the main chain. State channels work by performing the following 3 steps. 1. First, a part of the blockchain state is locked under a smart contract, ensuring the agreement and business logic between participants. 2. Now, off-chain transaction processing and interaction is started between the participants that update the state only between themselves for now. In this step, almost any number of transactions can be performed without requiring the blockchain. This is what makes the process so fast and arguably the best candidate for solving blockchain scalability issues. It could be argued that this is not a real on-chain blockchain solution, such as, for example, sharding, but the end result is a faster, lighter, and more robust network that can prove very useful in micropayment networks, IoT networks, and many other applications. 3. Once the final state is achieved, the state channel is closed, and the final state is written back to the main blockchain. At this stage, the locked part of the blockchain is also unlocked. This process is shown in the following diagram. This technique has been used in the Bitcoin Lightning Network and Ethereum's Raiden. The key difference between Lightning and Raiden is that Lightning only works for Bitcoin transactions, whereas Raiden supports all ERC-20 compliant tokens, making the Raiden network a more flexible option. Sidechains. Sidechains can improve scalability indirectly by allowing many sidechains to run along with the main blockchain, while allowing usage of perhaps comparatively less secure and faster sidechains to perform transactions, but that are still pegged with the main blockchain. The core idea of sidechains is called a two-way peg, which allows the transferal of tokens from a parent chain to a sidechain and vice versa. Subchains. This is a relatively new technique recently proposed by Peter R. Rizin and is based on the idea of weak blocks, which are created in layers until a strong block is found. Weak blocks can be defined as those blocks that have not been able to be mined by meeting the standard network difficulty criteria, but have done enough work to meet another weaker difficulty target. Miners can build subchains by layering weak blocks on top of each other, unless a block is found that meets the standard difficulty target. At this point, the subchain is closed and becomes the strong block. Advantages of this approach include reduced waiting time for the first verification of a transaction. This technique also results in a reduced chance of orphaning blocks and a speeding up of transaction processing. This is also an indirect way of addressing the scalability issue. Subchains do not require any soft fork or hard fork to implement but need acceptance by the community. Tree chains. There are also other proposals to increase Bitcoin scalability, such as tree chains, which changed the blockchain layout from a linearly sequential model to a tree. This tree is basically a binary tree that descends from the main Bitcoin chain. This approach is similar to sidechain implementation, eliminating the need for major protocol change or block size increase. It allows improved transaction throughput. In this scheme, the blockchains themselves are fragmented and distributed across the network in order to achieve scalability. Moreover, mining is not required to validate the blocks on the tree chains. Instead, users can independently verify the block header. However, this idea is not ready for production yet, and further research is required in order to make it practical. In addition to the aforementioned general techniques, some Bitcoin-specific improvements have also been proposed by Christian Decker. Much of Decker's work can be found here. scholar.google.ch/citations $user equals ZAE1ZIAAAJ &H1 equals EN in his book on the scalability and security of Bitcoin. This proposal is based on the idea of speeding up propagation time, as the current information propagation mechanism results in blockchain forks. These techniques include minimization of verification, pipelining of block propagation, and connectivity increase. These changes do not require fundamental protocol level changes. Instead, these changes can be implemented independently in the Bitcoin node software. With regards to verification minimization, it has been noted that the block verification process is contributed toward propagation delay. The reason behind this is that a node takes a long time to verify the uniqueness of the block and transactions within the block. It has been suggested that a node can send the inventory message as soon as the initial POW and block validation checks are completed. This way, propagation can be improved by just performing the first difficulty check and not waiting for transaction validation to finish. Plasma. Another recent scalability proposal is Plasma, which has been proposed by Joseph Poon and Vitalik Buterin. This proposal describes the idea of running smart contracts on the root blockchain, Ethereum mainnet, and having child blockchains that perform high numbers of transactions to feed back small amounts of commitments to the parent chain. In this scheme, blockchains are arranged in a tree hierarchy with mining performed only on the root main blockchain, which feeds the proof of security down to child chains. This is also a layer 2 system since, like state channels, Plasma also operates off-chain. Commit chains. Commit chains are a more generic term for Vitalik Buterin's Plasma proposal. They are also referred to as non-custodial sidechains, but without a new consensus mechanism, as is the case with sidechains. They rely on main chain consensus mechanism so they can be considered as safe as the main chain. The operator of the commit chain is responsible for facilitating communication between transacting participants and sending regular updates to the main chain. ZK Rollups. ZK Rollups is a layer 2 solution that allows multiple transactions to be bundled into a single transaction. This approach enables mass transfer processing using a single transaction, which improves scalability. Trusted hardware-assisted scalability. This technique is based on the idea that complex and heavy computing can be offloaded to off-chain resources in a verifiably secure manner. Once the computations are complete, the verified results are sent back to the blockchain. Other scalability techniques include multi-chain approaches. One of the prime examples of such techniques is Polkadot, which we'll describe briefly later in this chapter in the context of interoperability. However, this mechanism also provides scalability. With this, we have completed our discussion of some of the many potential scalability improvements of blockchain. In the next section, we'll discuss privacy and some relevant techniques to achieve privacy in blockchain. Privacy. Privacy in blockchain can be divided into two main categories based on the type of service required. These categories are the anonymity of the users and the confidentiality of the transactions. Anonymity is concerned with hiding the sender's or receiver's identity, whereas confidentiality addresses the requirements of hiding transaction values. Anonymity. Anonymity is desirable in situations where the identity of users is required to be hidden from other participants on the network. This can be due to regulatory requirements, enterprise requirements, or just due to the sensitive nature of the transactions. For example, in a business network, it might be desirable to hide the dealings between different participants on the network from other competitors to avoid friction or unjustified business competitive advantage. The properties of unlinkability and untraceability are used to achieve anonymity. The property of untraceability allows for the hiding of the trace of a transaction from one party to another. On the other hand, unlinkability means that an observer is unable to deduce the link between transactions and its participants, or the relationships between transaction participants, senders, and receivers. We also discussed anonymity in Chapter 9, Alternative Coins, in greater detail. Confidentiality. Confidentiality is an absolute requirement in many industries such as finance, law, and health. Similarly, privacy of transactions is a much desired property of blockchains. However, due to its very nature, especially in public blockchains, Everything is transparent, thus inhibiting its usage in various industries where privacy is of paramount importance, such as finance, health, and many others. There are different proposals that have been made to address the privacy issue, and some progress has already been made. Several techniques such as indistinguishability, obfuscation, homomorphic encryption, zero-knowledge proofs, ZKPs, and ring signatures have all been researched and implemented. All of these techniques have their merits and demerits, and will be discussed in the following sections. Techniques to achieve privacy. In this section, we'll describe different techniques to achieve privacy, including anonymity and confidentiality. Similar to scalability solutions, we can also divide privacy solutions into three categories, based on the layer within the blockchain architecture stack that they operate. Layer 0 methods or network layer methods, where the mechanism to achieve privacy operates at a network level. Layer 1 methods, also called on-chain methods, where the blockchain protocol itself is enhanced to achieve privacy. Layer 2 methods or off-chain methods, where mechanisms that exist outside of the main blockchain are used to achieve privacy on the blockchain. As many of the techniques described in the following sections can be used at layers 1 and 2, for example, zero-knowledge proofs, we are not distinguishing between these layers. Instead, we'll only list these solutions and discuss what they can be used for. Furthermore, solutions for anonymity and confidentiality also overlap, and techniques used to achieve confidentiality are also more or less applicable in achieving anonymity. We do, however, segregate Layer 0, the network layer, and describe some of the network approaches to achieve anonymity, before moving on to introduce a range of privacy mechanisms that are applicable at layers 1 and 2. Layer 0. These solutions are network layer level methods that provide anonymity by using Tor and I2P. These methods allow for hiding the identities of the parties involved. Tor, the onion router, is a software that enables anonymous communications. More information on Tor is available here, torproject.org. We can use Tor to enable anonymous communication in cryptocurrency blockchain networks. Tor is a common choice to enable anonymous communication and has been used in Monero, Verge, and in Bitcoin to provide anonymity. For Bitcoin, see bitcoin.it/wiki/Tor. Monero can also be run with Tor, web.getmonero.org. Verge is another example of cryptocurrency making use of Tor for IP obfuscation. I2P, Invisible Internet Project, is an anonymous network built on the Internet. It enables censorship-resistant peer-to-peer communication. It is used in Monero to provide anonymity services. More information on I2P is available here, geti2p.net/en. Layers 1 and 2. Other layers include Layer 1 and Layer 2 solutions, which we'll introduce next. Indistinguishability obfuscation. This cryptographic technique may serve as a silver bullet to all privacy and confidentiality issues in blockchains. But the technology is not yet ready for production deployments. Indistinguishable obfuscation (IO) allows for code obfuscation, which is a very ripe research topic in cryptography. If applied to blockchains, I/O can serve as an unbreakable obfuscation mechanism that will turn smart contracts into a black box where the behavior of the obfuscated code is indistinguishable. In simpler words, the inner functionality of the smart contract is totally hidden. The key idea behind I/O is what's called by researchers a multilinear jigsaw puzzle, which basically obfuscates program code by mixing it with random elements, and if the program is run as intended, it will produce the expected output. However, any other way of executing it would make the program look like random garbage data. This idea was first proposed by Sanjam Garg et al. In their research paper Candidate Indistinguishability Obfuscation and Functional Encryption for All Circuits. Homomorphic encryption. This type of encryption allows operations to be performed on encrypted data, imagine a scenario where the data is sent to a cloud server for processing. The server processes it and returns the output without knowing anything about the data that it has processed. This is also an area ripe for research, and fully homomorphic encryption, which allows all operations on encrypted data, is still not fully deployable in production. However, major progress in this field has already been made. Once implemented on blockchains, it can allow processing on ciphertext, which will allow the privacy and confidentiality of transactions inherently. For example, the data stored on the blockchain can be encrypted using homomorphic encryption, and computations can be performed on that data without the need for decryption, thus providing privacy service on blockchains. This concept has also been implemented in a project named Enigma, which is available online at media.mit.edu/projects/enigma/overview by MIT's Media Lab. Enigma is a peer-to-peer network that allows multiple parties to perform computations on encrypted data without revealing anything about the data. Zero-knowledge proofs. ZKPs have recently been implemented in Zcash successfully, as seen in Chapter 9, Alternative Coins. More specifically, Succinct Non-Interactive Argument of Knowledge, SNARKs, have been implemented in order to ensure privacy on the blockchain. The same idea can be implemented in Ethereum and other blockchains also. Integrating Zcash on Ethereum is already a very active research project being run by the Ethereum Research and Development Team and the Zcash company. There is a recent addition to the family of ZKPs called Zero Knowledge Succinct Transparent Argument of Knowledge, ZK-STARK, which is an improvement on ZK-SNARKs in the sense that ZK-STARKs consume a lot less bandwidth and storage. Also, they do not require the initial, somewhat controversial trusted setup that is required for ZK-SNARKs. Moreover, ZK-STARKs are much quicker as they do not make use of elliptic curves or rely on hashes. Bullet proofs are non-interactive zero-knowledge short proofs. They require no trusted setup. This scheme allows a prover to prove that an encrypted number is within a range of numbers without revealing any other information about the number. State channels. Privacy using state channels is also possible, simply due to the fact that all transactions are run off-chain, and the main blockchain does not see the transaction at all except for the final state output, which ensures privacy and confidentiality. Secure multi-party computation. The concept of secure multi-party computation is not new and is based on the notion that data is split into multiple partitions between participating parties under a secret sharing mechanism, which then does the actual processing on the data without the need to reconstruct data on a single machine. The output produced after processing is also shared between the parties. Multiple parties carry out the computation mutually without revealing their inputs. Only the output of the computation is revealed. Trusted hardware-assisted confidentiality. Trusted computing platforms can be used to provide a mechanism by which confidentiality of a transaction can be achieved on a blockchain, for example, by using Intel Software Guard Extension SGX, which allows code to be run in a hardware-protected environment called an enclave. Once the code runs successfully in the isolated enclave, it can produce a proof called a quote, which is attestable by Intel's cloud servers. It is a concern that trusting Intel will result in some level of centralization and is not in line with the true spirit of blockchain technology. Nevertheless, this solution has its merits, and in reality, many platforms already use Intel chips anyway, so trusting Intel may be acceptable by some in some cases. If this technology is applied to smart contracts, then once a node has executed the smart contract, it can produce a proof of correctness, thus proving successful execution, and other nodes will only have to verify it. This idea can be further extended by using any trusted execution environment, TEE, which can provide the same functionality as an enclave and is available even on mobile devices with near-field communication, NFC, and a secure element. For example, Ikerin is a platform that makes use of Intel SGX's T to run smart contracts while preserving confidentiality. CoinJoin. CoinJoin is a technique that is used to anonymize Bitcoin transactions by mixing them interactively. The idea is based on forming a single transaction from multiple entities without causing any change in inputs and outputs. It removes the direct link between senders and receivers, which means that a single address can no longer be associated with transactions, which could lead to the identification of users. CoinJoin needs to cooperate between multiple parties that are willing to create a single transaction by mixing payments. Therefore, it should be noted that if any single participant in the CoinJoin scheme does not keep up with the commitment made to cooperate for creating a single transaction by not signing the transactions as required, then it can result in a DOS attack. In this protocol, there is no need for a single trusted third party. This concept is different from mixing a service, which acts as a trusted third party or intermediary between the Bitcoin users and allows shuffling of transactions. This shuffling of transactions results in the prevention of tracing and linking payments to a particular user. Confidential transactions. Confidential transactions make use of Peterson commitments in order to provide confidentiality. Commitment schemes allow a user to commit to some value while keeping it secret with the capability of revealing it later. Commitment schemes can be constructed simply by using cryptographic hash functions. Two properties that need to be satisfied in order to design a commitment scheme are binding and hiding. Binding makes sure that the committer is unable to change the chosen value once committed, whereas the hiding property ensures that any adversary is unable to find the original value to which the committer made a commitment. A Peterson commitment is a type of information hiding, computationally binding commitment scheme under a discrete logarithm assumption. Peterson commitments allow for additional operations and preserve commutative property on the commitments, which make them particularly useful for providing confidentiality in Bitcoin transactions. In other words, they support partial homomorphic encryption of values, meaning that using commitment schemes allows the hiding of payment values in a Bitcoin transaction. Mimblewimble. The Mimblewimble scheme was proposed somewhat mysteriously on the Bitcoin IRC channel and since then has gained a lot of popularity. Mimblewimble extends the idea of confidential transactions and CoinJoin, which allow the aggregation of transactions without requiring any interactivity. However, it does not support the use of the Bitcoin scripting language, along with various other features of the standard Bitcoin protocol. This makes it incompatible with the existing Bitcoin protocol. Therefore, it can either be implemented as a sidechain to Bitcoin or on its own as an alternative cryptocurrency. This scheme can address both privacy and scalability issues at once. The blocks created using the Mimblewimble technique do not contain transactions as in traditional Bitcoin blockchains. Instead, these blocks are composed of three lists: an input list, an output list, and something called excesses, which are lists of signatures and differences between outputs and inputs. The input list basically references the old outputs, and the output list contains confidential transaction outputs. The blocks created using the Mimblewimble scheme are verifiable by nodes by using signatures, inputs, and outputs to ensure the legitimacy of the block. In contrast to Bitcoin, Mimblewimble transaction outputs only contain pub keys, and the difference between old and new outputs is signed by all participants involved in the transactions. Mixing protocols. A mixing protocol or mixer is a service that allows users to preserve their privacy by mixing their coins with other users. We discussed mixers in detail in Chapter 9, Alternative Coins. Attribute-based encryption. The attribute-based encryption, ABE, is a type of public key cryptography that provides confidentiality and access control simultaneously. The key idea behind this scheme is that the private key of a user and its ciphertext are dependent on the user's attributes such as their location, time zone, or their role in the organization. This means that the decryption is only possible when not only the private key is available, but also the matching attributes are present. Anonymous signatures. Anonymous signatures are types of digital signatures where the signatures do not reveal the identity of the signer. There are primarily two schemes available for anonymous signatures: group signatures and ring signatures. Group signatures allow a set of signers to form a group managed by a group manager. Each member of the group is issued with the group signing key by the group manager. This group signing key allows each member of the group to anonymously sign messages on behalf of the group. The group manager is able to figure out who is the signer of the message, whereas external entities cannot. While group signatures can work well, one of the limitations of this scheme is that the group manager is able to identify the users. This issue was addressed with ring signatures. Ring signatures allows a set of signers to form a group, a ring of members. Each member in this group is able to sign messages on behalf of the ring. Unlike group signatures, there is no group manager in ring signatures, so no one is able to identify the signers. While all these techniques are useful and provide many desirable properties of anonymity, there is also a problem of using this technology maliciously. Imagine if anonymity is misused by criminals involved in money laundering or selling illegal drugs by using anonymous cryptocurrency. It would be almost impossible to trace illegal activities back to the originator if absolute anonymity is achieved. Imagine a Silk Road marketplace variant using anonymous cryptocurrency. How could that be traced and stopped? Privacy managers. Privacy managers provide a mechanism that provides confidentiality of transactions. These are off-chain components that substitute the transaction payload with a hash index in such a way that only those participants who are party to the transaction are able to find the corresponding encrypted payload represented by the hash index. Other parties who are not privy to the transaction will simply ignore the hash. This concept was discussed in Chapter 20, Enterprise Blockchains. We can visualize many of the blockchain privacy techniques discussed so far in this chapter using the following chart. Other than scalability and privacy, there are several other general security aspects that need to be addressed in blockchain. We'll describe these general security topics next. Security. Blockchains are generally secure and make use of asymmetric and symmetric cryptography as required throughout the blockchain network to ensure that the core layer of the blockchain is secure. However, there still are few caveats that can result in compromising the security of the blockchain. There are a few examples of transaction malleability, eclipse attacks, and the possibility of double spending in Bitcoin that, in certain scenarios, have been shown to work by various researchers. Transaction malleability opens up the possibility of double withdrawal or deposit by allowing a hacker to change a transaction's unique ID before the Bitcoin network can confirm it, resulting in a scenario where it would seem that transactions did not occur. BIP62 is one of the proposals, along with SegWit, that has suggested solutions to solve this issue. It should be noted that this is a problem only in the case of unconfirmed transactions, that is, scenarios where operational processes rely on unconfirmed transactions. In the case of normal applications that only rely on confirmed transactions, this is not an issue. Information eclipse attacks in Bitcoin can result in double spending. The idea behind eclipse attacks is that the Bitcoin node is tricked into connecting only with the attacker node IPs. This opens up the possibility of a 51% attack by the attacker. This has been addressed to some extent in Bitcoin Client version 0.10.1. More information on the attack and how it has been fixed is available here. cs-people audiobooks.bu.edu/Heilmann/Eclipse. Now, before discussing security further in blockchains, let's have a look at the interesting topic of formal verification. This is becoming a hot topic in blockchain space due to its strong technical merits as a technique to address security issues. Note that this is not a new technique, but it has found very interesting applications in blockchain technology. Formal verification. Before diving into different formal verification techniques that are available in blockchain space, first let's develop some understanding of what formal verification is, what its types are, and why it is desirable. Formal methods are the set of techniques used to model systems as mathematical objects. These methods include writing specifications in formal logic, model checking, verification, and formal proofs. Generally, formal methods can be divided into two broad disciplines called formal specifications and formal verification. The first discipline is concerned with writing precise and concrete specifications, whereas the latter encompasses the development of proofs to prove the correctness of a specification. In essence, formal verification is comprised of 3 steps. 1. First, creating a formal model of the system to be checked. 2. Secondly, write a formal specification of the properties that are expected to be satisfied by our model. 3. Finally, the model is checked to ensure that the model satisfies the specification. For checking, there are 2 broad categories of techniques that can be used, namely state exploration-based approaches and proof-based approaches. There are pros and cons to both. State exploration-based approaches are automatic but are inefficient and difficult to scale. A usual problem is state explosion, where the number of states to check grows so exponentially big that the model does not fit in a computer's memory. On the other hand, proof-based approaches, theorem proving, are more precise but usually require human interaction and more in-depth knowledge of the proofs and relevant techniques. In the next section, we'll introduce a formal verification technique called model checking, which is used to check a system model for its correctness. Model checking. Model checking can be defined as a technique used to verify finite state systems automatically. The underlying process is based on running an exhaustive search of the state space of the system. With this brute force approach, it can be determined whether a specification is true or false. This option is becoming more popular because it does not require time-consuming proof writing. Instead, this paradigm allows a designer to write the specification formally and its properties, and the model checker will automatically explore the entire state space and evaluate the model against the specified properties. For example, if the specification says that a particular state should never be reached and during state exploration, the model checker finds that there is an execution trace that does enter that very state that is undesirable, then it will report that. The designer can then address the problem accordingly. A visual representation of the model checking process is shown in the following diagram. The process of model checking starts with modeling, where a formal specification is created from an informal design of the model. The specification step comes next, where relevant properties of the design are specified using some logical formalism. Finally, verification of the model is carried out, which checks all the properties defined in the specification and provides results. In the case of false or negative outcomes, error traces with counterexamples, roughly defined as exceptions, are provided to help the designer trace the error. Mathematical assertion languages called temporal logics are used to describe states of a system over time. Temporal logic is used at the specification step of the model checking process, which represents the evolution of the behavior of a system over time, or in this case, the ordering of events of a system over time. In this paradigm, a specification of the behaviors of the system over time is built using various fundamental properties of individual states. For example, in a state, it can be said that something is on or something is active. There are also propositional connectors used in the specification's design, such as and, up or down, not, and imply. We will use these connectors in some basic examples shortly to demonstrate how they can be used in conjunction with formulas to describe system properties. Finally, there are also temporal connectives, which issue statements like the system can always only have one process active, or the system can never be in a state where both read and write operations are performed simultaneously. There are two types of temporal logics, namely linear temporal logic (LTL) and computation tree logic (CTL). LTL is concerned with the model properties on a single computation path or execution, whereas CTL is used to express properties over a tree of all possible paths. There are a few fundamental temporal operators used in LTL to describe a system's behavior. These properties can be used to specify the safety and liveness properties of a system. The formulas are P always, P eventually, U until, and 0 next. The always and eventually properties are most commonly used. For example, message signed, sealed, valid means if a message is not signed or sealed, then it is always the case that the message is not valid. Another example could be broadcast received, meaning that broadcast always implies that eventually the message will be received. Another general example could be that of a microwave oven, ensuring that heating must not start until the door is closed, which can be represented in temporal logic as start heating U door closed. Formal methods are needed to ensure the safety of a system and have been in use in the avionics, electronics, hardware, and embedded systems industries for quite some time, and most lately in the software industry. Due to renewed interest in distributed systems, research with the advent of blockchain, and several high-profile incidents resulting in financial loss, such as the infamous DAO hack, the need to use formal methods in the blockchain space is becoming increasingly prominent. Some initiatives have already taken place. However, there is still a long way to go. Blockchain needs to leverage on the research that has already been done in distributed systems and formal verification space, so that not only can existing blockchain systems be made safer, but new platforms can be developed based on formal specification. It should be noted that not all aspects of a blockchain need to or should be formally verified, due to the time-consuming and highly involved nature of the verification process. Therefore, at times, it is sufficient to model and test the most critical parts of a blockchain, such as consensus and security protocols. There are many dimensions in blockchain where model checking and specification using temporal logics can be quite useful. It can be used to describe an aspect of the blockchain platform formally, which can then be verified formally to ensure that all required properties are met. For example, in smart contract development, regardless of the language used, a model could be developed and checked before the actual coding of the smart contract. This approach will ensure that the program code, if programmed correctly according to the verified specification, will behave as it is intended. As smart contracts are used in all kinds of critical use cases, including financial transactions, it is advisable to apply model checking in this domain to ensure fairness and security of the system. Now, we'll briefly look at how consensus mechanisms can be verified. Verifying consensus mechanisms. From another angle, a consensus mechanism such as PBFT exists in a blockchain, which ensures that all the nodes in a blockchain network reach an agreement on the proposed values, even in the presence of faulty nodes. This is an area of prime importance, and due to its critical nature is regarded as the most vital core mechanism of a blockchain. Model checking can play a crucial role in the formal description and verification of consensus algorithms to ensure that the protocols meet the required security properties. A general approach to verifying properties of a consensus algorithm in blockchain starts from specifying the requirements, required properties, and specification in a formal language. A distributed consensus algorithm is evaluated against two categories of correctness properties, namely safety and liveness. Safety generally means that nothing bad will happen, whereas liveness implies that something good will eventually occur. Both of these properties then have some sub-properties, depending on the requirements. Usually for consensus mechanisms, we have agreement, integrity, and validity attributes under safety properties, and for liveness, often termination is a desired property. We can say that a program is correct if, in all possible executions, the program behaves correctly according to the specification. The specification is formally defined, which is then verified using a model checker or theorem provers. Static analysis allows us to check the code against a set of coding rules to find code defects. The code does not execute instead, it is statically checked. On the other hand, there is a dynamic analysis technique where the code is executed to find bugs and tested against test criteria. Dynamic analysis usually constitutes unit test and is not considered a formal verification technique. Static analysis using formal techniques is used to formally verify the correctness of the program. With this, we've completed our basic introduction to formal verification. Now, let's have a look at smart contract security and see what formal tools are available for smart contract security verification. Smart contract security. Recently, a lot of work has been started in smart contract security, and especially the formal verification of smart contracts is being discussed and researched. This was all triggered especially due to the infamous DAO hack. Formal verification is a process of verifying a computer program to ensure that it satisfies certain formal statements. This is not a new concept, and there are a number of tools available for other languages that achieve this. For example, Frama-C, frama-c.com is available for analyzing C programs. The key idea behind formal verification is to convert the source program into a set of statements that is understandable by the automated provers. For this purpose, Y3, which is a platform for program verification, is commonly used. We'll discuss Y3 at length in the Y3 topic later in this section. Smart contract security is of paramount importance now, and many other initiatives have also been taken in order to devise methods that can analyze Solidity programs and find bugs. A recent and seminal example is Oyente, which is a tool built by researchers to analyze smart contracts. Several security bugs in smart contracts have been discovered and analyzed in the Oyente white paper, making smart contracts smarter. These include transaction ordering dependence, timestamp dependence, mishandled exceptions such as call stack depth limit exploitation, and reentrance vulnerability. The transaction ordering dependency bug basically exploits the scenarios where the perceived state of a contract might not be what the state of the contract changes to after execution. This weakness is a type of race condition. It is also called front-running, and is possible due to the fact that the order of transactions within a block can be manipulated. As all transactions first appear in the memory pool, the transactions there can be monitored before they are included in the block. This allows the transactions to be submitted before another transaction, thus leading to controlling the behavior of a smart contract. Timestamp dependency bugs are possible in scenarios where the timestamp of the block is used as a source of some decision-making within the contract, but timestamps can be manipulated by the miners. The call stack depth limit is another bug that can be exploited due to the fact that the maximum call stack depth of EVM is 1024 frames. If the stack depth is reached while the contract is executing, then in certain scenarios the send or call instruction can fail, resulting in non-payment of funds. The reentrancy bug was exploited in the DAO attack to siphon out millions of dollars into a child DAO. The reentrancy bug essentially means that a function can be called repeatedly before the previous first invocation of the function has completed. This is particularly unsafe in Ether withdrawal functions in Solidity smart contracts. This is because block.timestamp, the withdrawal function, can call back into it repeatedly, without waiting for the first call to complete. More on this shortly in the Oyente section. In addition to the aforementioned bugs, there are several other problems that should be kept in mind while writing contracts, such as the fact that when sending funds to another contract, sending can fail, and even if throw is used as a catch-all mechanism, it will not work. Timestamp dependence is another vulnerability that is quite common. Usually the timestamp of a block is accessed via now or block.timestamp. But this timestamp can be manipulated by miners, leading to influencing the outcome of some function that relies on timestamps. Often this is used as a source of randomness in lottery games to select the next winner. Thus, it might be possible for a miner to modify the timestamp in such a way that its chances of becoming the next winner increase. Other usual software bugs such as integer overflow and underflow are also quite significant, and any use of integer variables should be carefully implemented in Solidity. For example, a simple program where uint8 is used to parse through elements of an array with more than 255 elements can result in an endless loop. This occurs because uint8 is limited to 256 numbers. Smart contracts and generally all aspects of blockchain can be formally verified. In the following sections, examples of contract verification will be shown using Remix IDE, Y3, and Oyente. Static analysis in Remix IDE. Static analysis of Solidity code is now available as a feature in the Solidity Online Remix IDE. The code is analyzed for vulnerabilities and reported in the Analysis tab of the Remix IDE. A sample output of a contract with reentrancy bug is shown at the bottom of the preceding screenshot. Static analysis in Remix IDE analyzes several categories of vulnerabilities, including security and gas and economy. As shown in the preceding screenshot, the analysis tool has successfully detected the reentrancy bug, details of which are shown at the bottom of the screen. Other than static analysis capabilities within the Remix IDE, other tools are also available, such as Y3, which we'll discuss next. Y3. Y3 can also be used for formally analyzing Solidity code. In the following example, a simple piece of Solidity code that defines the z variable as the maximum limit of uint is being shown. When this code runs, it will result in returning 0 because uint z will overrun and start again from 0. This can also be verified using Y3, which is shown here. Conversion from Solidity to Y3 compliant code used to be available in Solidity's online compiler, but it is no longer available. Therefore, the following example is only for completeness purposes and to shed light on an important class of bugs that can go undetected with traditional tools. In this example, integer overflow is shown as an example. The following example shows that Y3 successfully checks and reports integer overflow errors. This tool is under heavy development but is still quite useful. Also, it should be noted that tool, or any other similar tool, is not a silver bullet. Even formal verification generally should not be considered a panacea. This is because specifications in the first place should be defined appropriately. In the preceding screenshot, the Y3 IDE is shown with a smart contract being analyzed for issues, which are reported on the right-hand side. In this case, an integer overflow has been found, which is reported. In the next section, we'll see how a different tool, Oyente can be used to test a smart contract for security vulnerabilities. Oyente. Currently, Oyente is available as a Docker image for easy testing and installation. It is available at github.com/melonproject/oyente and can be downloaded and tested. In the following example, a simple contract taken from the Solidity documentation that contains a reentrancy bug has been tested. First, we will show the code with a reentrancy bug. This sample code contains a reentrancy bug, which basically means that if a contract is interacting with another contract or transferring ether, it is effectively handing over the control to that other contract. This allows the called contract to call back into the function of the contract from which it has been called, without waiting for completion. For example, this bug can allow calling back into the withdraw function shown in the preceding example again and again, resulting in obtaining ether multiple times. This is because the share value is not set to 0 until the end of the function, which means that any later invocations will be successful, resulting in withdrawing again and again. An example is shown of Oyente running to analyze the contract shown here, and, as can be seen in the following output, the analysis has successfully found the reentrancy bug. The bug is proposed to be handled by a combination of the checks effects interactions pattern described in the Solidity documentation. Oyente is also available in the analysis tools for smart contracts at oyente.melonport.com. A sample output is shown here. With this example, we conclude our introduction to security and analysis tools for Solidity. This is a very rich area of research, and more tools are expected to be available with time. There are many experts and researchers in academia and the commercial sector exploring this area, and soon there will be many automated tools available for the verification of smart contracts. There is an online tool available ready at securify.ch that analyzes smart contract code to find security vulnerabilities. Now, we'll discuss some other tools that we can use to analyze smart contracts for correctness and security vulnerabilities. Other tools. Other relevant tools and research in the security arena of blockchain technology include SolGraph, Manticore, and other tools for formal verification of smart contracts. SolGraph. This tool generates a graph of function control flow of a Solidity contract and finds possible security vulnerabilities. More information on this tool is available here. github.com/rain/solgraph. Manticore. This is a symbolic execution framework that can be used for binaries and smart contracts. Symbolic execution is a method used to analyze computer programs to determine which part of the computer program executes as a result of what input. In other words, it establishes which input executes which part of the program. In symbolic execution, instead of actual input data, symbolic values are used, which are then used to evaluate the program. Also, an automated theorem prover is used to check whether there are values that result in incorrect behavior of the program or cause it to fail. It is used for debugging, software testing, and security. Formal verification of smart contracts. A lot of research on formal verification of smart contracts have also been conducted. The proposed techniques include, but are not limited to, model checking, static analysis, dynamic analysis, and verification using proof assistance. Some of the more relevant papers on the subject include the following. After all this discussion on smart contract security, we should now understand its significance. While all the issues and techniques discussed here to mitigate the security issues in smart contracts are valuable, a question still arises about what else we can do, given that smart contract security is a sensitive topic that can result in serious financial losses. The answer could be that we treat smart contracts and the underlying blockchain as safety-critical systems, and then apply all attributes of safety-critical systems to smart contracts. From an engineering perspective, it will become a subject of safety-critical systems and will be treated as such. This idea might sound a bit over the top, but imagine if, one day, a smart contract is responsible for generating an event that would trigger a shutdown as a result of overheating in a nuclear reactor. Again, a little exaggerated perhaps, but entirely possible with IoT and blockchain convergence. Such scenarios might become a reality, where nuclear reactors are running using a blockchain as a mechanism to control and track associated operations. Now, we'll introduce some other challenges that blockchain technology faces, which should be resolved in order to enable the mainstream adoption of blockchain. Other challenges. In addition to key issues such as privacy and scalability, there are a few other challenges that can hinder the adoption of blockchain as a mainstream technology. We'll discuss these challenges and some possible solutions next. Interoperability. We discussed interoperability briefly earlier in this book. It is sufficient to say here that interoperability is an open challenge, and while many initiatives such as Cosmos, Polkadot, and Interledger are in progress to address this limitation, there is still a long way to go. One of the approaches is standardization of blockchain protocols, thus making them compatible with one another. Another approach is to develop protocols that will make existing blockchains interact with each other, such Interledger. We cover Cosmos and Interledger in detail in this book's bonus content pages here. In this section, we will briefly describe Polkadot. Polkadot is a platform that allows connectivity between different private and public chains, oracles, and many other technologies. It is a platform used to enable Web3, a decentralized web, and allows any type of data to be exchanged between any type of blockchain. It offers heterogeneous sharding, scalability, upgradability, transparent governance, and cross-chain composability. The key concept behind Polkadot is a relay chain, which is responsible for cross-chain interoperability, consensus, and overall network security. Polkadot allows communication between different independent blockchain shards called parachains. Parachains connect to the relay chain after paying a fee. Other components include bridges, which are a special type of blockchain that enable connectivity of parachains with outside networks such as Bitcoin and Ethereum. From a consensus perspective, there are several elements in Polkadot. Validators secure the chain by staking tokens called DOTs. DOTs provide governance, staking, and bonding. DOT holders are allowed to participate in governance activities such as protocol upgrades. Staking with DOTs provides a mechanism to ensure the security and stability of the Polkadot network. Also, bonding using DOTs allows new parachains to be added to the network. Overall, in the Polkadot network, validators secure the chain and are selected by nominators due to their trustworthiness. Collators maintain shards, and so-called fishermen operate on the network for monitoring and policing purposes. Lack of standardization. Lack of standardization leads to disparate systems that are unable to communicate with each other. This leads to interoperability issues. Therefore, there is a need to develop a common understanding of the requirements in order to develop blockchain platforms to the same standard. Doing this will ensure that all platforms are interoperable. Post-quantum resistance. With the advent of quantum computers, it is envisaged that soon cryptography used in blockchain will be at the risk of becoming less secure. This is due to the ability of quantum computers to work at phenomenal speed, allowing cryptanalysis of most of the schemes currently in use. There is already some work being done in order to secure blockchains against post-quantum attacks, but there is still a lot to do. Ethereum 2.0 is also ensuring that its chosen cryptography is either quantum secure or pluggable with quantum-secure counterparts when available. Also, quantum-resistant signature schemes such as Extended Markle Signature Scheme, XMSS, and SFIN-CS are being investigated for Ethereum 2.0. The beacon chain's RANDAO is also expected to be quantum-resistant. Compliance and regulation. Compliance and regulation are important aspects. In traditional IT systems, compliance and regulation plays a vital role in ensuring that data and information are handled in accordance with the policies, rules, and standards set by regulatory authorities. Adhering to such standards minimizes the possibility of security breaches, unauthorized access to data, and other issues stemming from the improper handling of data. Now, blockchain can, in fact, help to achieve compliance with certain regulations such as GDPR and other use cases, where tamper-resistant auditing of logs is required. A lot of work has already been done in the context of cryptocurrencies and tokens, but not so much from the underlying blockchain perspective. Treating cryptocurrencies and tokens as securities, allowing them to be governed by existing securities laws is one thing, but regulating the underlying blockchain technology in terms of adherence to security standards, data sovereignty, and information sharing regulations is another. We discuss compliance in detail in Chapter 20, Enterprise Blockchains. With this, we have completed our examination of different challenges that blockchain faces, and also discussed some of the current solutions available to address these challenges during the next stages of blockchain evolution. Summary. In this chapter, we introduced the various challenges facing blockchain technology. A major challenge, blockchain's limited scalability, was discussed, along with several methods available to achieve greater scalability. We approached these methods using different models which divide the blockchain into planes, or layers that can be improved in different ways. We also discussed privacy, which is one of the major limiting factors toward adopting public blockchains for various enterprise use cases. Next, we explored smart contract security and various tools to improve it, such as model checking. Formal verification is a deep and extensive subject, but a brief introduction to various aspects was given, which should serve as solid ground for further research in this area. We also saw examples of formal verification to have an idea of what tools are available. Finally, we discussed some other challenges to consider for the future of blockchain, including the issue of standardization and pluggability, and the inevitable need for quantum resistance. In the next and final chapter of this book, we will explore the current landscape and future prospects of the blockchain technology. Chapter 22: Current Landscape and What's Next. Blockchain technology is changing rapidly, and it will continue to affect the way we conduct our day-to-day business as new developments emerge. It has challenged existing business models and promised great benefits such as cost savings, efficiency, and transparency. So far in this book, we've explored the technical underpinnings of blockchain technology, such as cryptography, consensus mechanisms, and distributed systems concepts. We've looked at cryptocurrencies such as Bitcoin, Litecoin, and Zcash, explored Ethereum in detail, and learned how to write smart contracts and dApps. We also saw applications of blockchain technology in the Internet of Things, IoT, and the finance, government, and media sectors, and learned how blockchain technology can address challenges in these industries and others. Moreover, we examined Hyperledger and some innovative enterprise blockchains such as Quorum and Corda. Finally, we looked at some scalability, privacy, and security challenges faced by proponents of blockchain technology, and considered how these challenges can be tackled. This chapter will explore the latest developments, emerging trends, issues, and future predictions about blockchain technology. We'll also present some topics related to open research problems and improvements related to blockchain technology. Along the way, we'll cover the following main topics: emerging trends, areas to address, blockchain research topics, blockchain and AI, the future of blockchain. With the advancement of blockchain technology and the rigorous research being conducted in this space, various developments have been seen in recent months and years. We'll explore these emerging trends in the next section. Emerging trends. Blockchain technology is in a period of rapid change and intense development, due to the deep interest in it by the academic and commercial sectors. As the technology has become more mature, a few trends have started to emerge. For example, private blockchains have recently gained a lot of attention due to their specific use cases in finance organizations. Similarly, enterprise blockchains aim to develop blockchain solutions that meet enterprise-level efficiency, security, and integration requirements. For an in-depth exploration of the technical details and features of some alternative blockchains and their relevant platforms, take a look at this book's bonus online content pages here. These are out of the scope of this chapter, but it is highly recommended to access these pages to explore some recent blockchain solutions in more detail. Now, some of the broader trends are listed and discussed in the following sections. New implementations of blockchain technology. Since the invention of Bitcoin, new blockchains are being developed at a rapid rate. We'll introduce some of these new trends as follows. Application-specific blockchains. Currently, an inclination toward application-specific blockchains, ASBCs, is evident, whereby a blockchain or distributed ledger is specially developed or makes use of an already existing blockchain platform but with only one application in mind and is focused on a specific industry. For example, Everledger is a blockchain solution that has been developed for the sole use of providing an immutable tracing history and audit trail for diamonds and other high-value items. This approach thwarts any fraud attempts because everything related to ownership, authenticity, and item value is verified and recorded on the blockchain. This ability would be invaluable for insurance and law enforcement agencies were it to be widely adopted. Another example of an ASBC is Digital Trade Chain, DTC, in which a group of 7 banks agreed to simplify the trade finance process by directly connecting the parties involved in a trade transaction. Concrete, real-life, end-to-end implementations of blockchain technology are also now becoming available, even in the finance industry, such as Australian Securities Exchange, ASX, replacing its legacy post-trade system. Its system to support trade processing after completion, also referred to as trade settlement, with blockchain. Startups. In recent years, many technology startups have emerged that are working on blockchain projects. There has also been a significant increase in the number of startups that are offering blockchain consultancy services and solutions specific to this technology. Technology improvements. As well as innovative implementations of blockchain technology, a lot of effort is being made to improve the technology and infrastructure itself. Some of these efforts are listed in the following sections. Standardization. Blockchain technology is not yet mature enough to be able to readily integrate or interact with existing systems or other blockchains. And as it stands, no 2 blockchain networks can easily interact with one another. Standardization will help to improve interoperability, adoption, and integration aspects of blockchain technology. Some attempts have been made recently to address this, the most notable of which being the establishment of ISO TC 307, which is a technical committee with the aim of standardizing blockchain and associated distributed ledger technology. The aim of the committee revolves around increasing interoperability and data interchange between users, applications, and systems. Hyperledger, on the other hand, has a reference architecture that can be used to build blockchain systems based on the same modular architecture. Hyperledger is supported by the Linux Foundation and many other participants from the industry, which is a good omen for the progress of blockchain standardization. Some work on smart contract templates was started with the publication of a seminal paper authored by Christopher D. Clack, Vikram A. Bakshi, Lee Brain et al., which formally defined smart contract templates. It also presented a vision for future research and stipulated certain necessities in smart contract development. All of the efforts mentioned here are a clear indication that in the near future, clearly defined standards will emerge that will further advance the adoption of blockchain technology. Standardization will also result in exponential growth of the blockchain industry by eliminating hurdles such as interoperability. Consortia. Recent years have seen the startup of various consortia and shared open source efforts. This trend is expected to grow in the coming years, and more consortia, committees, and open source efforts towards blockchain advancement will likely emerge soon. A prime example is R3, which developed Corda with a consortium of some of the world's largest financial organizations. Enhancements. Various enhancements and suggestions to further develop existing blockchains have been made over the last few years. Some of these suggestions have been made in response to specific security vulnerabilities and to address inherent limitations in blockchain technology. There are certain limitations in blockchain technology, such as scalability, privacy, and interoperability, which need to be addressed before it can be adopted as a mainstream field of technology. Recently, there have been tremendous efforts made toward addressing scalability issues in blockchain technology, which were discussed in Chapter 21, Scalability and Other Challenges. Also, blockchain-specific improvement proposals such as Bitcoin Improvement Proposals, BIPs, and Ethereum Improvement Proposals, EIPs, are regularly made by developers to address various concerns in these systems. Moreover, recent advancements such as state channels, an off-chain scalability solution discussed in Chapter 21, Scalability and Other Challenges, are evidence of the fact that blockchain technology is improving rapidly and will, in time, evolve into a mature and practical technology. Using state channels, the Bitcoin Lightning Network and Ethereum's Raiden have been developed to enable near-distant, low-fee, scalable payments that could help address the scalability issue on future blockchain projects. Limitations around the interoperability of blockchains have also resulted in changes oriented toward the development of systems that can work across multiple blockchains. Some examples of these systems are Interledger, Polkadot, and Cosmos. Interledger has also been implemented in Java as Hyperledger Quilt. Moreover, various new blockchain solutions to the privacy issue have emerged, such as Cadena, which directly addressed blockchain confidentiality issues. Other concepts such as Zcash, CoinJoin,Zether, bulletproofs, and confidential transactions have also been developed to address existing blockchain privacy challenges. Another necessary enhancement is to reduce electricity consumption. It is evident from the global electricity usage of Bitcoin's blockchain that proof-of-work mechanisms are very inefficient. Of course, this computation secures the Bitcoin network, but there is no other benefit of this computation, and it wastes a lot of electrical energy. To reduce this waste, there has been more focus on greener options such as proof-of-stake algorithms, which do not need enormous reserves of resources like Bitcoin's POW algorithm does. This trend is expected to grow, especially with the implementation of a POS mechanism in Ethereum 2.0. This trend of addressing technical challenges is expected to continue to develop in years to come. And even if almost all fundamental challenges are addressed in blockchain technology, further enhancements and optimization research will continue. Ongoing research and study. Blockchain technology has stimulated intense research interests, both in academia and the commercial sector. In recent years, interest has dramatically increased, and now major institutions and researchers around the world are exploring this technology. This growth in interest is primarily because blockchain technology can help to make businesses and their operations more efficient, cheaper to run, and more transparent. The bulk of academic interest lies in addressing problems in the fields of cryptography, consensus mechanisms, and performance limitations in blockchains. As blockchain technology comes under the broader umbrella of distributed systems, many academic researchers focused on distributed computing research have focused their research on blockchain technology. For example, University College London has a dedicated department, the UCL Research Center for Blockchain Technologies, which focuses on blockchain technology research. Another example of academic groups conducting blockchain research is the ETH Zurich Distributed Computing Group, who have published seminal research regarding blockchain technology. A recent journal called the Ledger Journal has recently published its first issue of research papers. Another organization called the Initiative for Cryptocurrencies and Contracts, IC3, is also researching smart contract and blockchain technologies. IC3 aims to address performance, confidentiality, and safety issues in blockchains and smart contracts, and runs multiple projects to address these issues. As well as those mentioned here, there are now teams and departments dedicated to blockchain research and development in various academic and commercial institutes. Although the initiatives mentioned here are not an exhaustive list by any stretch of the imagination, it is still a solid indication that this is a subject of extreme interest for researchers, and more research and development is expected to be seen in 2020 and beyond. With the progress of blockchain adoption, research in different areas of cryptography has been conducted, with the aim of addressing challenges such as privacy. Some of these research directions are discussed in the following sections. Cryptography. Even though cryptography was an area of keen interest and research for many decades before Bitcoin's invention, blockchain technology has resulted in a renewed interest in this field. With the advent of blockchains and related technologies, there has been a simultaneous and significant increase in the interest in cryptography. New research is being carried out and published regularly, especially in the area of financial cryptography. Technologies such as zero-knowledge proofs, fully homomorphic encryption, and functional encryption are being researched for their potential use in blockchains. Already, ZKPs have been implemented for the first time at a practical level in the form of Zcash, which has addressed privacy issues in cryptocurrency networks. It's evident that blockchains and cryptocurrencies have helped with the advancement of cryptography, especially financial cryptography. Other developments such as Tether, zk-SNARKs, zk-STARKs, bulletproofs, the Aztec protocol, Nightfall, and Socrates are only the foundations of what the future holds for blockchain cryptography. Cryptoeconomics. New fields of research are emerging with blockchains, most notably cryptoeconomics, which is the study of protocols governing the decentralized digital economy. With the continuing development of blockchains and cryptocurrencies, research in this area has also grown. Cryptoeconomics has been defined by Vitalik Buterin as a combination of mathematics, cryptography, economics, and game theory. Hardware development. When it was realized in 2010 that contemporary methods were no longer efficient for mining bitcoins, miners shifted toward optimizing available mining hardware. These initial efforts included the use of GPUs, and then field programmable gate arrays were used after GPUs reached their hash rate limit. Very quickly after that, application-specific integrated circuits, ASICs, emerged, which increased mining power significantly. This trend is expected to grow further with research into optimizing ASICs by parallelizing and decreasing their die sizes. Such optimizations will make ASICs even faster and more efficient. Moreover, GPU programming initiatives are also expected to grow, with the regular emergence of new cryptocurrencies, many of which make use of POW algorithms that can benefit from GPU processing capabilities. For example, recently Zcash has spurred interest in GPU mining rigs and related programming using NVIDIA, CUDA, and OpenCL. The aim with Zcash is to use multiple GPUs in parallel to optimize mining operations. Also, some research has been done in the field of trusted computing hardware such as Intel's Software Guard Extensions, SGX, to address security issues on blockchains. Intel's SGX has also been used in a novel consensus algorithm called Proof of Elapsed Time, POET, which was discussed in Chapter 17 Hyperledger. Another project, the 21 Bitcoin computer, was developed, which serves as a platform for developers to learn about Bitcoin technology and develop applications for the Bitcoin platform. Hardware research and development is expected to continue, and soon many more hardware applications will be explored. Some examples include physical unclonable functions, the acceleration of blockchain processes, such as cryptography, IoT hardware, and hardware security module integration for key management. Formal methods and security. With the realization of security issues and vulnerabilities in smart contract programming languages, and generally in blockchain protocols, there is now a keen interest in the formal verification and testing of smart contracts and other blockchain components before production deployments. For this, various efforts are already underway, many of which we discussed in Chapter 21, Scalability and Other Challenges. New programming languages. There is also an increased interest in the development of programming languages for developing smart contracts. Efforts are more focused on domain-specific languages, for example, Solidity for Ethereum and Pact for Cadena. This is just a start, and many new languages are likely to be developed as the available technology advances. Education and employment within blockchain. While blockchain technology has spurred a great interest among technologists, developers, and scientists throughout almost every industry around the world, initially there was a lack of formal learning resources and educational material available for aspiring blockchain professionals. However, there has been a recent trend emerging in job markets whereby recruiters are seeking blockchain programmers and developers. This is especially relevant to the finance industry, in which many startups and even large organizations have started to hire blockchain specialists. There is also concern about the lack of blockchain developers, which will undoubtedly be addressed as the technology progresses, and more developers either gain experience on a self-learning basis or gain formal training from training providers. Consequently, many educational institutes around the world now offer certificates and courses with a focus on blockchain technology. This trend is, of course, expected to grow as the technology matures and is applied in more commercial use cases. Innovative blockchain applications. Some new ideas for improving the efficacy of blockchains have emerged with the unprecedented development of blockchain technology. Some of these are listed in the following sections. Blockchain as a service. With the current maturity level of cloud platforms, many companies have started to provide blockchain as a service, BaaS. The most prominent examples are Microsoft's Azure, in which the Ethereum blockchain is provided as a service, and IBM's cloud platform, which provides IBM's blockchain as a service. This trend is only expected to grow in the next few years, and more companies will likely emerge that provide BaaS to consumers. Electronic Government as a Service, EGaaS, which is in fact a form of BaaS, provides application-specific blockchains for governance functions. This project aims to organize and control activities without document circulation and bureaucratic overhead. Convergence with other technologies. The convergence of other technologies with blockchain offers major benefits to both technologies. At their core, blockchains provide resilience, security, and transparency, which, when combined with other technologies, results in a very powerful complementary technology. For example, the IoT stands to gain major benefits such as integrity, decentralization, and scalability when implemented via a blockchain. Artificial intelligence is expected to gain numerous benefits from the implementation of blockchain technology. In fact, within blockchain technology, AI can be implemented in the form of autonomous agents, which can make rational decisions on behalf of humans. Some ideas of the benefits that the convergence of AI and blockchain can provide are listed as follows. The blockchain can share machine learning models in a secure and peer-to-peer manner. The blockchain can serve as an auditing layer for decisions made by AI. As AI and machine learning capabilities grow, blockchain can provide a mechanism to monitor and control any malicious behavior that an AI may manifest. While AI can be used for good, it can also be used by malicious actors. In this case, the blockchain can serve as a control mechanism to thwart any attacks. For example, all agents on a blockchain can be controlled under a consensus mechanism, and malicious Byzantine behavior can be handled as per the blockchain consensus protocol. AI can also benefit blockchain technology by enabling artificially intelligent smart contracts. AI can be applied to other components of a blockchain to achieve, for example, adaptive consensus mechanisms. These can, based on network conditions, readjust fault tolerance requirements and, as a result, enable a more efficient consensus mechanism. There are, of course, many more examples of innovative applications of blockchain in combination with the aforementioned technologies. Some of these will be discussed in detail in the blockchain and AI section of this chapter. Alternatives to blockchain. With the advancement of blockchain technology in recent years, researchers have started to think about the possibility of creating platforms that can provide guarantees and services that a blockchain provides. But without the need for an actual blockchain, this has resulted in the development of R3's Corda, which is not really a blockchain since it is not based on the concept of blocks containing transactions. Instead, it is based on the concept of a state object that transverses throughout the Corda network, according to the requirements and rules of the network participants that represent the latest state of the network. Other examples include IOTA, an IoT blockchain that makes use of a directed acyclic graph as a distributed ledger named Tangle, instead of a conventional blockchain formed of blocks. This ledger is claimed to have addressed scalability issues and implemented high-level security features that even protect against quantum computing-based attacks. It should be noted that Bitcoin is also somewhat protected against quantum attacks, because quantum attacks can only work on exposed public keys, which are only revealed on the blockchain if both send and receive transactions are made. Therefore, if the public key is not revealed, which is the case in unused addresses or addresses that may have only been used to receive Bitcoin, then quantum safety can be guaranteed. In other words, using a different address for every transaction protects against quantum attacks to a degree. Also, in Bitcoin, it is relatively easy to change to another quantum signature protocol if required. Hedera Hashgraph is another alternative to traditional blockchain. It is a distributed ledger that runs an asynchronous Byzantine fault-tolerant protocol for achieving consensus. It is claimed to be a faster and more efficient alternative to traditional sequential blockchain. Some debatable ideas. As with every new idea, some debate is inevitable. Some of the topics that have sparked debate are discussed as follows. Public versus private on the blockchain. Although private and enterprise blockchains are seen as a solution to achieving privacy and a way to address other enterprise concerns such as scalability and governance, some blockchain purists are not convinced, since centralization is viewed as a deviation from the core philosophy of blockchains. Decentralization proponents envisage that, in the future, public blockchains will be able to provide all of the features that are desirable in enterprise use cases such as privacy, scalability, and governance. Using the Ethereum mainnet for enterprise use cases is also possible. There have been some high-profile activities performed on the public Ethereum network, such as bond settlement. With Ethereum 2.0, the need for enterprise blockchains may diminish as the mainnet becomes capable of providing all required enterprise services. Also, with the availability of privacy solutions such as Nightfall, Aztec, and Zephyr, public blockchain may become the tool of choice for enterprise use cases one day, and private blockchains may not be as necessary as they were initially thought to be. On the other hand, there are a number of advantages that private and enterprise blockchains provide, as discussed in Chapter 20, Enterprise Blockchain. Therefore, it is not entirely true that private blockchains are redundant. Decentralization is seen as a concern by enterprises, and public chains, with their fully decentralized nature, are deemed unsuitable for enterprise use cases. In traditional systems for enterprise blockchains, participants can be held accountable for their actions, but in public blockchains, there is no centralized control or governance, meaning that in cases of disputes, nobody can be held accountable. This clash of interest might change, however, if public blockchains could introduce an optional governance mechanism to support enterprise governance needs. This feature could be achievable using smart contracts, where a governance layer is provided on top of the underlying blockchains in order to meet enterprise requirements such as access control, auditing, and security. Central bank digital currency. With the advent of blockchain and tokenization, there is now a lot of interest in digital currencies issued by central banks. This is a somewhat controversial subject amongst regulators, technologists, and economists, but nevertheless something that could soon be a reality. The key difference between cryptocurrencies and central bank digital currency is that CBDC is issued by a central bank as legal tender. Declared by a country's government, it is a digital form of fiat money, whereas cryptocurrency is more of a decentralized token of value, which is not backed by government regulation, law, or any monetary body. As well as the topics we've discussed in this section, there are some further notable projects and relevant development tools that have emerged as a result of rapid development in blockchain technology that are beyond the scope of this chapter. Readers can explore some of these by referring to the bonus content repository for this book at static.pact/cdn.com/download/altcoins_and_more_bonus_content.pdf. In the next section, we'll introduce some challenges and areas of concern that need to be addressed in order to achieve the mainstream adoption of blockchain technology. Areas to address. Apart from security and privacy, which were discussed at length in Chapter 21, Scalability and Other Challenges, several other less technology-based obstacles should be addressed before broad adoption of blockchains can be achieved. We'll introduce some of these more specific areas to address in the following sections. Regulation. Regulation is considered one of the most significant challenges to blockchain development. The core issue is that blockchains and their associated cryptocurrencies are not recognized as legal systems or forms of currency by any government. Even though in some cases blockchain tokens have been classified as having monetary value, for example in the US and Germany, they is still far from being accepted as regular currencies. Moreover, blockchains in their current state are not recognized by financial regulatory bodies as platforms that are stable or reliable enough to be used by financial institutions. There have been, however, various initiatives proposed by regulatory authorities around the world to research and set regulations. Bitcoin, in its current state, is fully unregulated, even though some attempts have been made by governments to tax it. In the UK, under the EU VAT directive, Bitcoin transactions are exempt from value-added tax. This may change after the finalization of Brexit, but capital gains tax may still be applicable in some scenarios. Some attempt by financial regulatory authorities to regulate blockchain technology is expected very soon, especially after the recent announcement by the UK's Financial Conduct Authority that it may approve some companies that are using blockchain for their business services. Another regulatory concern is that blockchain technology is not ready for production deployments. Even though the Bitcoin blockchain has evolved into a solid blockchain platform and is used in production, it is not suitable for every scenario. This is especially true in the case of sensitive environments such as finance and health. However, this situation is changing very quickly, and this chapter has already explored various examples of new blockchain projects that have been implemented in real life, such as the ASX blockchain post-trade solution. This trend is expected to grow as efforts are made to improve the associated technology and address technical limitations such as scalability and privacy. Security is also another general concern that has been highlighted by many researchers, which is especially applicable to the finance and health sectors. A report by the European Union Agency for Network and Information Security, ENISA, has highlighted some distributed ledger-specific concerns, including the need for regulation, auditing, control, and governance. Some concerns highlighted in the report also include smart contract management, key management, anti-money laundering regulations, and anti-fraud tools. Clearly, while blockchain is generally seen as a solution to many technical business challenges, it can also be misused. In the next section, we'll see some scenarios in which cryptocurrencies and blockchain networks are being used for illegal activities. Illegal activity. With the key attributes of censorship resistance and decentralization, blockchain technology can help to improve transparency and efficiency in many walks of life. However, the somewhat unregulated nature of blockchain technology means that it has the potential to be used for illegal activity. For example, consider a scenario where illegal content is published over the internet. Normally, it can be immediately shut down by approaching the relevant authorities and website service providers. But this is not possible in blockchains. Once something is there on the blockchain, it is almost impossible to revert. This means that any unacceptable content once published on the blockchain cannot be removed. If the blockchain is used for distributing immoral or illegal content, then there is no way for anyone to prevent it. This fact poses a serious challenge, and it seems that some regulation and control would be beneficial in this scenario, but it provokes the critical question: how can a blockchain be regulated? In this case, it may not be prudent to create regulatory laws first and then see if blockchain technology adapts, because this might disrupt innovation and progress. It may be more sensible to let the blockchain technology grow first in a similar organic manner to the internet. Then, when its user base reaches a critical mass, governing bodies can call for the application of regulations around the implementation and usage of blockchain technology. There are various real-life examples where the dark web is used in conjunction with Bitcoin to perform illegal activities. One example is the Silk Road online marketplace, which was used to sell illegal drugs and other contraband over the internet. It used Bitcoin for payments and was hosted on the dark web using URLs only visible with the browser called Tor. Although the Silk Road was shut down after years of effort by law enforcement agencies, other sites have emerged that offer similar services. As such, this activity remains a major concern. Imagine that an illegal website was hosted on IPFS, a P2P distributed and decentralized storage network built on a blockchain. There would be no easy way of shutting it down. It is clear that the absence of control and regulation can encourage illegal activity, meaning criminal enterprises like the Silk Road will keep appearing. Further development of totally anonymous transaction capabilities such as Zcash, while useful, in various legitimate scenarios could provide another layer of protection for criminals. Clearly, it depends on who is using the technology. Anonymity can be good in many scenarios, for example in the healthcare industry where patient records should be kept private and anonymous. However, it may not be appropriate if it can also be used by criminals to hide their activities. One solution might be to introduce intelligent bots, AAs, or even contracts that are programmed and embedded with regulatory logic. They would most likely be programmed by regulators and law enforcement agencies, and live on the blockchain as a means to provide governance and control. For example, a blockchain could be designed in such a way that every smart contract has to go through a controller contract, which scrutinizes the code logic and provides a regulatory mechanism to control the behavior of the contract. It may also be possible to get each smart contract's code to be inspected by regulatory authorities, and once a smart contract's code has a certain level of authenticity attached to it in the form of certificates issued by a regulator, it will be deployed on the blockchain network. This concept of binary signing is akin to the already established concept of code signing, whereby executables are digitally signed as a means to confirm that the code is bona fide and not malicious. This idea is more applicable in the context of semi-private or regulated blockchains, where a certain degree of control is required by a regulatory authority. For example, in finance, it means, however, that some degree of trust is required to be placed in a trusted third-party regulator, which may not be desirable due to the deviation from full decentralization. However, to address this, the blockchain itself can be used to provide a decentralized, transparent, and secure certificate issuing and digital signing mechanism. Privacy or transparency. There needs to be a fine balance between privacy and transparency. Too much transparency can result in undermining personal privacy. However, too much privacy can result in the loss of transparency. The choice between privacy and transparency is use case dependent. However, a state of equilibrium is highly desirable to provide the best solution for both requirements. Now, let's consider some research topics that are currently being explored by researchers in the space. Any student or researcher could use this list of topics as a starting point for their research. Blockchain research topics. While some major innovations have been made in blockchain technology in recent years, the area is still ripe for further research. Some selected research topics are listed in this section, with some information about existing challenges and the latest developments. Some ideas are also presented on how to address the issues facing these topics. Smart contracts. Significant progress has been made in this area aimed at defining the key requirements of smart contracts and developing templates for their production. However, further research is required in this area in order to make smart contracts safer and more secure. Cryptographic function limitations. Cryptography used in the Bitcoin blockchain is exceptionally secure and has stood the test of time. In other blockchains, similar security techniques are used, which are also very secure. However, specific security issues such as the possibility of the generation and use of duplicate signature nonces in elliptic curve digital signature schemes, leading to private key recovery attacks, collisions in hash functions, and vulnerability to quantum attacks that could break the underlying cryptographic algorithms remain an exciting area of research. Consensus algorithms. Research in POS algorithms or other alternatives to POW is also an important area of research. This is especially relevant due to the fact that the Bitcoin network's power consumption is expected to reach almost 69 terawatts by the end of 2020, which is equivalent to entire nations in terms of electricity consumption. Alternatives such as POS algorithms have already gained a lot of traction and are due to be implemented in major blockchains such as Ethereum's Casper. However, so far, POW remains the best option for securing a public blockchain. It has also been suggested that instead of performing an inefficient or single-purpose form of work, as is the case with Bitcoin's POW, the power of the network can be used to solve useful mathematical or scientific problems. Scalability. A detailed discussion on scalability has already been carried out in Chapter 21, Scalability and Other Challenges. Briefly, it is sufficient to say that while some progress has already been made, there is still a need for more research in order to enable on-chain scalability and further improve off-chain solutions such as state channels. Some initiatives, like increasing block size and using transaction-only blockchains without blocks, have been proposed that increase the capacity of the blockchain itself to address scalability issues instead of using side channels. Examples of implementations without blocks include the previously mentioned Tangle. This utilizes a DAG to store transactions as compared to traditional blockchain solutions where a block is used to store transactions. This makes it inherently faster as compared to block-based blockchains such as Bitcoin, where the waiting time between block generations is currently approximately 10 minutes. The performance increase comes from the fact that instead of mining a block, in a DAG-based system, transactions are linked to one another and are used for confirming and verifying the next transactions, instead of mining and verifying blocks. Code obfuscation. Code obfuscation using indistinguishability obfuscation can be used as a means to provide confidentiality and privacy in the blockchain. However, this is still not practical due to prohibitive computational complexity, and some major research efforts are required to achieve this. Now let's return to the subject of blockchain's technology's convergence with the IoT and AI for a more in-depth analysis. Blockchain and AI. It is envisaged that other technologies such as IoT and AI will converge for the mutual benefit and wider adoption of both blockchain and the other given technology. The convergence of blockchain with IoT has been discussed at length in Chapter 21, Scalability and Other Challenges. Briefly, it can be said that due to blockchain's authenticity, integrity, privacy, and shared nature, IoT networks would benefit greatly from making use of blockchain technology. This can be realized in the form of an IoT network that runs on a blockchain and makes use of a decentralized mesh network for communication in order to facilitate machine-to-machine, M2M communication in real time. All of the data that is generated as a result of M2M communication can be used in machine learning processes to augment the functionality of artificially intelligent DAOs or simple AAs. These AAs can act as agents in a blockchain-provided distributed artificial intelligence environment, which can learn over time using machine learning processes. This would enable them to make better decisions for the good of the blockchain. AI is a field of computer science that endeavors to build intelligent agents that can make rational decisions based on the scenarios and environment that they observe around them. Machine learning plays a vital role in AI technology by making use of raw data as a learning resource. A key requirement in AI-based systems is the availability of authentic data that can be used for machine learning and model building. Therefore, the explosion of data coming out of IoT devices, smartphones, and other means of data acquisition means that AI and machine learning is becoming more and more powerful. There is, however, a requirement for data authenticity, which is where the convergence with blockchain comes in. Once consumers, producers, and other entities are on a blockchain, the data that is generated as a result of interaction between these entities can be readily used as an input to machine learning engines with a guarantee of authenticity. It could also be argued that if an IoT device is hacked, it could send malformed data to the blockchain. This issue would be mitigated using blockchain technology because an IoT device would be part of the blockchain as a node and would have the same security properties applied to it as a standard node in the blockchain network. These properties include the incentivization of good behavior, rejection of malformed transactions, strict verification of transactions, and various other checks that are part of blockchain protocol. Therefore, even if an IoT device is hacked, it would be treated as a Byzantine node by the blockchain network and would not cause any adverse impact on the network. The possibility of combining intelligent oracles, intelligent smart contracts, and AAs will give rise to artificially intelligent, decentralized autonomous organizations, AI DAOs, that can act on behalf of humans to run entire organizations on their own. This is another side of AI that could potentially become normal in the future. However, more research is required to realize this vision. The convergence of blockchain technology with various other fields such as 3D printing, virtual reality, augmented reality, spatial computing, and the gaming industry is also envisaged. For example, in a multiplayer online game, blockchain's decentralized approach allows more transparency and can ensure that no central authority is gaining an unfair advantage by manipulating game rules. Each of these topics are currently active areas of research, and more interest and development is expected. Now, let's discuss the future of blockchain technology and make some predictions about its development. The future of blockchain. The year 2019 saw the move from the theoretical proof of concept stages to the production of some real-life blockchain environments. 2019 was also considered the year of enterprise blockchain, and it is expected that before the end of 2020, we will see more organizations implementing full-scale enterprise blockchain-based projects. The start of 2021 will likely see a significant rise in tokenization and ecosystems built around tokens. A prime example of mainstream tokenization use is DeFi, which currently has billions of dollars worth of value locked in its ecosystem. In the years to come, this technology is only expected to grow. In this section, to round off the chapter and give an idea of the scope of blockchain development, there are a few careful predictions based on current advancement and the speed of progress. All of these predictions are likely to be realized between the years of 2020 and 2050. The IoT will run on multiple blockchains and will give rise to an M2M economy. This will include energy devices, autonomous cars, and household accessories. Central bank-issued digital currencies will become a reality and will be applied in day-to-day use within the next 2 to 5 years. Within the next 3 to 5 years, DeFi will be regulated, having become part of regular financial activities, and will have hundreds of billions of dollars worth of value locked within its ecosystem. Medical records will be shared securely while preserving patient privacy between various private blockchains run by a consortium of health providers. It may well be a single private blockchain shared among all service providers, including pharmacies, hospitals, and clinics. Elections and voting systems will be managed transparently and securely via decentralized web applications, making use of a backend of blockchain technology. Financial institutions will run a multitude of private blockchains to share data between participants and to manage internal processes. Financial institutions will make use of semi-private blockchains that will provide identity information for controls and functions such as AML and Know Your Customer (KYC). This will be shared between other financial institutions around the world. Immigration, passport control, and border control related activities will be recorded and conducted on a blockchain, shared between all ports of entry and border agencies around the world. Governments will run interdepartmental blockchains to provide core services such as pension and benefits disbursement, and to monitor land ownership records, birth registrations, and other database services. This way, auditability, trust, and a sense of security will develop between citizens and their governments. Publicly available regulated blockchains run by governments will be used on a day-to-day basis by citizens in order to manage their digital identities and perform their day-to-day activities. for example, tax payments, TV license registrations, and marriage registrations. Research in cryptography and distributed systems will reach new heights, and universities and other educational establishments will offer dedicated courses on cryptography, cryptoeconomics, and blockchain technology. Artificially intelligent DAOs will become part of blockchains, which will make rational decisions on behalf of humans for the good of the system that they are part of. BaaS will be provided as standard to anyone who wishes to run their business or day-to-day transactions on a blockchain. In fact, it's entirely possible that just like the internet, blockchains will seamlessly integrate into our daily lives, and people will use them without knowing anything about the underlying technology or infrastructure. Blockchains will commonly be used to provide digital rights management services for media and the arts, and will be used to deliver content directly to consumers. This will enable direct communication between the consumer and producer, eliminating the need for a central party to govern the licensing and rights management of valuable goods. Existing cryptocurrencies such as Bitcoin will continue to grow in value, with the availability of state channels and scalability efforts. This trend is only expected to grow. Bitcoin's value will likely reach tens of thousands of US dollars per BTC. As a result, cryptocurrency investment will greatly increase, and a new crypto-economic system will emerge. Financial institutions and clearinghouses will start to introduce blockchain-based solutions as part of the normal process for their customers. Blockchains are going to change the world. The revolution has already begun, and it is only expected to continue. Summary. First, in this chapter, a few trends were discussed that are expected to continue as the technology progresses. We also explored some areas outside technology that will have to be addressed before the blockchain is accepted into society, such as its use in legal activity. Some research topics were suggested that are being pursued by researchers and organizations around the world, and should be considered for personal research by any student or academic. Furthermore, convergence with other fields such as the IoT and AI were also explored. Finally, some predictions regarding the growth and adoption of blockchain technology were made. Most of these predictions are likely to come true within the next decade or so, while some may take longer. Blockchain technology has the potential to change our lives, and the impact is already noticeable. This growth is evident in the form of successful POC implementations and production deployments. Moreover, the number of enthusiasts and developers taking an interest in this technology is increasing, a reflection of the fact that blockchains are becoming intertwined with our lives, just as the internet has been for decades. This chapter was only a modest overview of the vast and tremendous potential of blockchains, and further adoption and applications of this technology are inevitable as it matures. In this book, we have explored the technical foundations of blockchain and learned how to build practical, real-world decentralized applications. We've explored cryptocurrencies, alternative blockchains, enterprise blockchain, scalability, and privacy, and examined the underlying mechanics of blockchain technology. We've combined these theoretical foundations with practical development, design, and deployment of blockchain networks, smart contracts, and decentralized applications. We learned how to use Truffle, Ganache, Drizzle, and other tools and techniques to build the apps. Moving forward, detailed accounts of tokenization, consensus mechanisms, and recent developments, such as Ethereum 2.0, were provided. Blockchain can arguably be considered the most innovative technology of this decade, and as we've seen throughout this book, it is one of the most active areas of study by researchers, academics, and now you. You are now capable of applying the knowledge from this book and continuing your learning to try your hand at entry-level blockchain development or architecture. With the material provided in this book, you are equipped with the necessary skills and knowledge of blockchain technology to participate in further research and development concerning this amazing technology, and be part of the blockchain revolution. This has been Mastering Blockchain, a deep dive into distributed ledgers, consensus protocols, smart contracts, dApps, cryptocurrencies, Ethereum, and more. 3rd edition, written by Imran Bashir, narrated by Telefrias Jr. Copyright 2020 by Imran Bashir. Production copyright by Vital Publishing LLC.